Hi, welcome back. This is the last in a series of 10 live streams on power theory. And the plan for this afternoon is to type up some of the stuff that we've learned. So we've had a whole bunch of adventures through the worlds of ring theory and Galois theory, and I'm going to try and make some summary notes of what that's been like, so that at the end I've got something to refer back to. I'm not quite sure how I'm going to show you this while I'm doing it. This is kind of the mathematician thing about typing up notes. It's going to involve a lot of latex, so I guess we're going to learn that a little bit as well. Learning experience for everyone. Okay, here's how I think I'm going to do it. I think we're going to get the map there. So I'm going to look at my notes that I've been working on all week, but I'm going to type things, not there, but over on here. Let's see if I can switch. Yeah, okay. That's cropped super weirdly. Why has that done that? Can I get that better? Yeah, why is it so wide? Why is it like this? Is there a crop on it? So this is the place where I'm going to type up some notes for this afternoon. I'm just trying to make it like, I know that Twitch sometimes does those kind of like streams where someone's coding up stuff. And I think I want to try and do that sort of setup. But to make it more fun, I want to let you see what I'm doing. Right, okay, so I can do this. I need to resize the actual window to be the right, like that. Like that, and then resize the window, and then scale it in here, and then it fits in there. That's all nice. Left, right, there we go. Just put it there, and then I've got a window where I can show you what I'm typing. Okay, so this is LaTeX, by the way. This is a place to type stuff up. So I'm going to take the and I can flip between them. I can show you both. Here we go, mathematician setup. I've got these notes, which I'm going to try and type up into here, nice and tidy. So first, let's go. We've got our root of least resistance. Oh, we're going to find out that my typing is terrible. That's just something that's going to happen, I suppose. So we've got a kind of intro section, which is going to look at what a group is, what a ring is, what a field is, what a vector space is. So I'm going to have all of those going through here, and so there's going to be an introduction of some stuff over here, and then there's going to be a section here that a field with a subfield is like a vector space. Okay. And then we need to introduce some sort of notions about polynomials. So section down here on polynomials. I'm not sure that we're going to define irreducible and separable. Maybe we are. Irreducible means the idea that you've got can't be factored. And then we've got this idea of separable, which means that you have no repeated roots. And then hiding in here, we've got this idea about highest common factor. So polynomials form a ring, and then you've got because you can add and multiply them, brackets. And then the next idea I want to bring in is this idea about, so from the notes, there's a thing where we would like to talk about highest common factor. So like polynomial division or highest common factor. And then further down, we want to do this sort of trick for detecting repeated roots. This is kind of cool. Further down there, we're going to now the idea to quotient by a polynomial which reminds me that up here for groups, we should do this idea of quotient by a normal subgroup. Oh, come on, typing. Up there. Quotient by polynomial. Ring quotients, do we want to talk about that? Only in the context of quotienting by polynomial, I think. Yeah. So up here, quotient by normal source and the isomorphism theorem to say that a kernel of a map is a normal subgroup. Quotient by polynomial, and then quotient by an irreducible polynomial gives a field by, so this is like a polynomial ideal, and then this is irreducible polynomial ideal. When I say quotient by a field, I kind of really mean quotienting by the ideal generated by that polynomial. Okay. Let's clean this up a bit. Okay, terrible messy note. It's going to get better over the course of the afternoon, I think. Plan is to try and make this not so terrible. So then it's time to have the idea of keep going to make the splitting field, which has all the roots equal in number to the degree of the polynomial over here, because no repeated roots or something with some other stuff in there. Okay. Now I've remembered that I want to talk about subfields and the Tower law, which I think does go up here. Intermediate field gives three sorts of vector space Tower law for the sizes. So the notion of a vector space here needs to include the idea of dimension. Okay. So, introduction, and then down here, so let's make that a section. This is a subsection. This is a subsection. I think it should be plural. Subsections down here for fields, and then vector space needs to include the notion of a dimension, and then intermediate fields. You got maybe like this section is going to be like vector spaces from fields. You can make them in a couple of different ways. And then there's this new section about polynomials, yeah, which has got all these tricks in it. And the idea of quotienting by polynomial and getting fields. And you can keep going. So now you're generating new fields for your polynomial. That's the stuff about polynomials. And then there's going to be a section on Galois extensions, which is going to be defined. So define we've got kind of three equivalent definitions, and we do want all three. Do we want all three? We kind of want to use two equivalent definitions, because we're never going to use the normal and separable one on its own. We're going to use the L to the can I introduce my own notation for this, because it's quite clumsy in a way. Quite clumsy. I kind of wanted to define it as like the fix of. Yeah, let's try something like that. Ooh, is it two S's in AMS sim? Can you complain at me? work? No, it's not how it works. You have to make the title. I like having the date on here. Okay. Oh, I hate the way it makes this huge gap, but never mind. Okay, space here for laying out how we're going to explain these things and build vector field spaces out of fields. And then polynomial facts, and then Galois extensions. One of them is going to be that let's just try and go for it. The invariance of L under the Galois group is equal to K. So, no, I feel like I should look at or I might put lots of new lines in when I'm just putting up my notes to start off with. Or we've got this idea that L over K is the splitting field for some separable polynomial. Let's double check that because I think I'm making mistakes already. So over here to look at the nodes. There it is. So over here we've got field extension L over K is Galois extension given us is the splitting field for a separable polynomial over K. So we're going to have the idea of when we introduce those intermediate fields, or even when we introduce the subfields, we're going to say, this notation, subfield, write LK if L if K is a subset of L and they're both fields. And sometimes we'll use that to sort of mean L with merely a reminder that K is the sub being treated as is a subfield. Pronounce it. L over K. So then this invariant thing, I hate this already. So this one is my main definition, and then I've got K is precisely the set fixed by all the automorphisms. So I've got to really define automorphisms at some point, which reminds me that back up in groups I'm supposed to have cyclic groups. Examples to include cyclic groups. Okay. So we've got two equivalent definitions down here. Oh, I need to find a Galois group. Or so what are those automorphisms? Yeah. So we kind of want automorphisms in first. Or L over K with all automorphisms. Try and put it in words. Maybe I shouldn't put it in words. Maybe I should just put L invariant or for now or K L equals K. And there's a beautiful notation there not to write out the I of K. Right. How much do I believe that? I want to set up a new operator, I think. How do you do this? I've forgotten how you do this. As always, Google it if you don't know. Declare operator? Declare math operator. Where does it live? It's on MS Math. Yeah. Declare math operator. What are the arguments of declare math operator? Nope. Declare math operator. It's got two arguments. We'll go. Oops. And then do I put this one in here? What do I put in? Good typing, proper font and spacing. Myop. Declare math operator. Myop. Ort like that. And let me go. Ort. Yes, it does. Excellent. Good. Always love a declare math operator. And then I kind of want to consider writing this. And then my new math operator is like the invariance fix or the invariance. So I find that power very confusing. So why not write it as the invariance of L under the automorphisms, like that. Why is it now unhappy with ort? It's just being silly, isn't it? Oh, don't be like this. Okay. Maybe that's just too wide, right? Invariance of L under the automorphisms. And then I also need to explain what automorphisms are. Automorphisms K for L means maps L to L which respect addition and multiplication and also fix each element of K. And then there's a note because these are good. Okay, oh, I'm not showing you what I'm typing, but you know. Typed a load of stuff. Did some declare math operator, it was great fun. Things sometimes happy with me, sometimes unhappy with me about my automorphism definition. Okay. And then there's a gap here for proof that these are equivalent, and it's technical. But then what do we want? We want down here. Oh, morning. Hi. I'm typing up my own notes now. It's going so well that I'm writing up my own stuff based on my understanding of Galois groups. Based on this kind of schematic of how to get through just to the Quintic straight away. So I'm currently typing up, roughly just trying to tidy this up because this page is super messy, right? There's everything I think you need in order to get down to the Quintic. So hopefully the doc that I'm typing up should hopefully be a guide that introduces groups, rings, vector spaces, fields, for people who haven't seen those terms before, and then goes kind of quite directly to Galois theory and just the bits that you need in order to get to why Quintics don't have a general solution. Having done the quest and it got to the point where I feel like I understand it well enough, now I want to just write up a kind of subset of it. So technical proof that these two definitions of Galois groups are the same thing, which is this sort of thing in here with the tautology, and then we need to build understanding. So building the understanding over here is the idea that, so in the notes, we want to go to something like it. Okay, note that these automorphisms must fix 0 because there's gaps in here for me to fill in with maths, right? Note that these automorphisms must fix 0. Note that, and then the rough thing that I'm going to say here is that polynomials are preserved in K, are preserved. And then there's something here like gamma from the group of P of X. X in there? I'm not sure. Equals P of gamma of X or something. And then something like since only 0 gets and then only. It's a ton. I have to grade exams. Oh no. Well, what sort of exams? What course? Or just all of maths? I suppose I don't know what level you're teaching. School exams? Or like, it's not Galois theory, right? It could be worse. Don't tell me you teach Galois theory. Please don't tell me you teach Galois theory. Or maybe do. Automorphisms fix 0 because in K and only send 0 to 0. Alright, like basic algebra can mean a lot of different things, but I think I know what you mean. Common mistakes? What sort of stuff? Are we talking like a plus b squared? Or matrices and vector space. Oh yeah, okay, cool. Yeah, good stuff, right, okay, I've got to explain vector spaces at some point in these notes. Look at this weird empty gap I've got up here where I'm supposed to be explaining vector spaces. Since only 0 gets sent to 0, roots get sent to roots by the automorphism. So there's kind of this idea that Galois group permutes the roots kind of idea down here. And then say more in there, so ... to flesh that out quite a lot more. Okay, now what we want to do is kind of demo maybe. Demo with the automorphisms over R of C. So once to fix every element of R that makes mess around with C is kind of there are lots of maps C to C. It's kind of a thing that's too stupid to put in the actual lecture notes, right? I guess lots of maps C to C, but not very many automorphisms. In particular, roots of now for the particular FBFC is the splitting field. It really is for x squared plus 1 over the reals. So roots plus or minus I must be sent to roots, and there's only one non-trivial way to commute them, and there's only, let's go, that feels bad to single out the trivial permutation. Only two ways to commute them. Oh, I always use right arrow. Am I being, I've never tried 2. What does 2 look like? Oh. 2 looks the same to me. I'm like, is that one larger than the other or not? Oh, and I've done a BF instead of a BB there. Good. Shortcut. I don't know, I've always used right arrow. Huh. That's 2. There we go. Double shortcut. Thank you. Learning. Yeah, literally nothing changed. Okay. Right, notes. So, I got these ideas, and then also, that's the same one though, so maybe not that. Suppose, oh, we've moved some size stuff down. Tower law, where do I want to put the tower law? Oh, it's kind of the vector space stuff, isn't it? The intermediate field? Yeah, no, we already have the tower law in this version. Yeah, I've already put the tower law in. It's gone up. And then I want to talk about the size of the automorphism. So maybe this is a subsection or something. The size of board. Okay. Now, not very exciting typing happening here, but there you go. Size of that. And then there's this bit from, I'm going to adapt section 3.15, excuse me, theorem 3.15 or something, using for automorphisms. No, but I've got to do, before I do 3.15, yeah, no, 3.15 is how you're going to count them, and that needs the tower law. So this is pretty technical. And a kind of L equals M equals J version. That's pretty technical, but gives you the size related to the dimension, which we're going to need for the stuff to do with the quotient law and the subgroup stuff. So back to the notes. Down here, successive Galois extensions. Here is the kind of bit where we start talking about formulas. So maybe this is a section on formulas for roots. And then I guess what I want to try and convince people is that having a formula is like successive Galois extensions. Because and then there's some stuff that's just, the notes don't say this because it's maybe too obvious, but are all field operations, so that's fine and not really an extension. And maybe you want to do nth roots. So there's super rough notes at the moment. Nth roots. Oh, it's unhappy with me because I didn't close enough of these. So like the minus sign maybe? Oh, it's not like I doesn't like divide. Where's the tech for division symbol? Not in typing. Div. That's sort of safely unguessable. There we go. That'd be, yeah, a long dash for an actual subtraction sign. There we go. Divide by non-zero elements. Maybe. Maybe you want to do an nth root. That's just like extending to the roots of some A in your field. That's just like extending to the roots of x to the n minus A Gower extension index equals that. Okay, extending to those roots. And then successive Gower extensions. So now we go to the fundamental theorem of Gower theory. I suppose successive Gower theory. Gower. So as you built Gower extension out of a sequence of Gower extensions, ending with one final triumphant extra extension. Then you have K, something in subset, K subset L subset M with all three of those fields, and with K subset M, so I want M over K and M over L and M over, and K, L over K, all Galois extensions. So you do some polynomial stuff all the way through. So the crucial bit, final triumphant extra extension. How do you do? Do you take a by? I don't do enough set theory on LaTeX. I don't know what all the symbols are. Subset Ek. There we go. All Galois extensions. Now, what do I want? I'm not yet going to say without loss geometry through with roots unity first. I'm going to say this needs to be the aha normal subgroup step, which I'm calling aha normal subgroup because that's what it says in my scribbled notes. Somewhere in here I have aha normal subgroup theorem 4.4. Yeah, the key part of that plan, you see, the key part of that plan is to actually get around to improving it later. If you're not careful, if you're like me and you're lazy, then you just end up with terrible notes. And so long as you remember not to publish the terrible notes, then you're probably fine. But don't let perfection stop you from just typesetting something like aha normal subgroup into your document. You know, I'm going to get rid of it at some point probably, but it helps me keep it quite casual all the way through. This is also the rush through of trying to get down to where I'm going with this. Check that it's in the right order at least. What are we doing? Normal subgroup. Yeah, so this is the, so via inclusion map homomorphism, kernel is the group that fixes M, the intermediate, which one's intermediate for me? L, intermediate field. Aha, for aha normal subgroup. Good stuff. Now, there needs to be a section here that talks about roots, nth roots. I think everyone does. Nth roots. It's natural, especially if you're broadcasting live on Twitch or something. It's tempting to just want to put out. I mean, part of broadcasting live on Twitch means that I'm not just putting out the perfect final version. I'm forced to put out the rubbish thing where I spell words wrong and stuff. I've got 60 times a second. I'm putting a version out there. It's good for me. Embracing imperfection at 60 FPS. Oh God, That's not the tagline. That cannot be the tagline. Let's put it in. Embracing imperfection. Embracing imperfection 60 times per second. Censor it. Oh, when that censor come on? It's in a close braces or anything. Fine, I'll do it properly. There we go. Okay, down here, roots. Okay, so I had to convince people up here that doing it there. So this is going to be something like, let's look more at that that particular polynomial, that one. And suppose you already fixed. Suppose you already included the roots of unity. Then there's some stuff on Kummer extension stuff to say the Galois group of, yeah, I've changed my mind. N is now prime all the way through. Some prime P. And this sentence doesn't really make sense anymore, but whatever. Then Kummer extension stuff. Galois group of the extension for those roots is just so it could be trivial, right? It could be trivial if you already had them secretly. Roots of unity. So yeah, let's go for a subgroup of CP, the cyclic group. Spell it out. Cyclic group with a P. So abelian. Oops, we need to define that. Let's go commutative. Let's just go commutative throughout. Have normal subgroups, or am I not? Trivial. And then here is maybe the good place to do the S5 example. Has A5 as a normal subgroup, but then no further normal subgroups of A5. This structure is important later, because that's what's going on down there. Now, okay, so if let's say you added the roots of unity, close bracket, roots of unity first, and then you did all your Pth roots, then your Galois group that you made has a chain of, this is the chain of cyclic quotients, chain of normal subgroups, cyclic quotients, and then punchline. That's called solvable. Not all groups like that we saw above S5. And then down here is a section on Quintic. And for the Quintic, you need to go and convince me, have a quick look. For the Quintic, you need to convince me that Quintic, you need to convince me that the particular Quintic, and I'm going to write out the one from the lecture notes, I might at some point choose my own, has two complex, exactly three real roots. Complex conjugation is an automorphism, so we should have talked about it before. Not that I'm aware of for solvable groups. Yeah, I'd be surprised if there was a different sort of definition or a good equivalent way, because at least this is the right one to think about for Galois theory, if there are some sort of other ways to think about solvable groups. This is the right way to think about those groups for Galois theory, because the Galois extension stuff generates this chain of stuff. You're doing these successive extensions, throwing in extra roots. So a kind of successive chain of nature is the right way. So if there was maybe a nice way, I agree that then that would be good for looking at a group and saying, is that solvable? There might be better ways of doing that. Hard question at the end then, deciding which groups are solvable. Yeah, I don't know. Yeah. No, I agree it's a question. Can you just detect solvable groups by like counting their elements and dividing by 2 or something, right? Not in this course, I don't know. I suspect probably not, but again, what do I know? Transposes roots. So no. And corresponds here to transposition. On the other hand, now, gosh, if we actually generated the splitting field in the manner described above, first step would be to quotient by px, and that would give something of degree 5. There are perhaps further quotients, further extensions to go to get the other roots, but by the Tower law, we know that 5 will divide the overall dimension or degree of the extension to the splitting field. There's an element of order 5, and that has a lovely proof about socks. So this is a permutation group. This is a subgroup of S5. This is going to be an apology at the start, I think. So this is a subgroup of S5 that has an element of order 5, a 5 cycle, and a transposition. So it's everything. You can make everything like that. It's weak. So the Galois group. The Galois group really is S5 in this case. That's not simple, so cannot be constructed by a chain. I want to use that word again. A chain of Galois extensions, e.g. from a chain of radical extensions. Chain of can't really say this down here, but because I haven't defined radical extensions, I'm going for the finish line now. So how do I feel about this? kind of want to move the lovely proof about socks. I need an apology here. The Galois group, the automorphisms, the splitting field of this. We'd like to show that the actual Galois group is rich and complex. To do that, rather than trying to describe the automorphisms directly over the rather complicated splitting field, we can make some observations. The cubic has exactly 3 real roots, not the identity, which might happen if it had real roots. First step is quotient by p of x. That will give something in degree 5. So up here, when we do our quotients ages ago, quotient degree is dimension of that, of the vector space is the degree of the polynomial all the way up here. Okay, so it's pretty healthy at the moment. We've got very tersely laid out 3 and a bit pages. I hate the kind of default margins. So I'm going to fiddle with that, which is not that important. Oh, elementary problem of the solution. Oh, it does not require Galois theory all this time, all this quest. You don't have to understand any Galois theory at all. Let's kind of look that up. I went all this way. Quintic, elementary. Oh, and it's got some nice notes. Okay. Here's a doc that we found on the web. Oh, and you've linked me in chat as well. Yeah, I'm on that page too. Cycle notation. It's about functions. What is going on with this then? Loops. Loops reduces the permutation. Oh, this was nice stuff then. Finite combination. Okay, commutative loop which reduces. Right, okay. Ooh, about nesting level. Arnold, 1963. A quintic formula about a field operation continuous function of radicals. So nesting of level bigger than or equal to n. Oh wow, okay, infinite degree. Maybe I should put this on screen since I'm reading it, I'm mumbling. And select the thing that I'm reading and cut so you can see it. There we go. Oh, So the exciting bit down here is talking about radicals having at least nesting level, defined as this number of square root sort of things you nest inside each other. Group. Shapes of the roots. General. Okay. That sounds good. A stronger result. You can also throw in sine and exponentials. Much more straightforward. So semester's work. Yeah, okay. Our semester's work is what we're kind of trying to do this week. Yeah, okay. Huh. This proof was over 500 pages long. Arbel did a 6-page proof, and I've heard that was because, yeah, anyway. Cass ignored an early manuscript of Arbel. Brilliant stuff. Okay. Suitable written version. Most famous written version in the books, tiny version of paper. Former is hundreds of pages long. Sophisticated. Huh. Ooh, then there's a YouTube video. Which channel is that one? Great stuff. Oh no, what have I done? I've duplicated. I've gone back. Stop me being live. What do I think about this? I think I'm going to read this. We're studying a PDF on the web now. It's good. Oh, I guess a commutator of 2 parameters. Oh my goodness. There is still some group theory in here. Jesus. Don't any abstract group theory. Okay. Go and check them all. Check all 120 squares combinations of pairs. What is this? Okay, let's go to the top and see what's going on. Yeah, cycle notation. Convenient notation, describe permutation of objects. Right, okay, so not abstract Galois theory. Yeah, okay, cycle notation, good. Yep, I know about that already, actually. It tells you where things go. 4 goes to 3, 3 goes to 1, and then it loops, 1 goes to 4. You can put them together. Intuition. Okay. It's working. Oh, this toy is working. Ooh. 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 What is this doing? Coefficients and roots. Okay, so all my coefficients are real. My roots are pairing complex conjugates. Nice. Then if I move them round, you get to do weird and complicated stuff, right? Oh, someone's getting quite close together. Okay, I don't know what intuitions that's building, but hey. Left is coefficient space. There are 2 dots labelled root space. Oh, okay, move it around. Oh, move A0 in a big loop. Roots R1 and R2. Wait, what? A big loop and the roots go. Wait, okay, so let's put the roots, put the other coefficients in here. This says if you take A0 a complex coefficient and you move it around, the roots rotate by 1 step. That's amazing. That's really nice. You end up at the same place, same roots. Let's make the roots look a bit more extreme. Like this. Extreme roots. This is really good. Thank you, person in chat. Oh my goodness, what? So now are they not swapping the permutations? Oh no, they're getting really close together. They are. That one is going over there. That one's coming back. Just make them move around. Wait. It really feels like that bottom right one is not moving. Oh, it is moving. It's just going super fast at some point there. Okay, right, I love that. I don't really understand what's going on. This is really, really weird. This is amazing. Yeah. Root says not function. Okay, so like square rooting. Right, okay, so this is what we're playing with, is maybe the way that you go around and the cycling group goes. Why isn't the root to the vertex of a regular polygon with sets at 0? Yeah, I suppose these roots, the coefficients are really weird, so they're not just, the equation here is not just x to the n equals 1. The roots could in general be anything when you have coefficients just all over the place. If you have real coefficients, or if you have all of them at 0 or something. Which one do I want? I think I want A3 to be non-zero. Then you get something more like a square, right? If I stick all of these at 0. Something more like a square. Alright, yeah. Somebody else was here this morning talking about how it's hard to imagine in general this thing about, oh, you can move these. Good, oh, you can move these. This is very good. I'm having a lot of fun with this. Right, good, okay. Going back to the website, set the degree of polynomial 3, maneuver the coefficient so it's this. Label these three roots, move A around a different loop. We can at least induce at least 2 permutations. Oh, so you're also going to let me do ones like this where I just go around one of the, just go around like that and just do a swap of some of these, or just over here do a swap of those two, or over here just do a swap. Well, it doesn't look like it's swapping anything if I go around A3. Either this, go round, what's that doing? If I do a loop around both of these, this is amazing. I can't really tell what it's doing anymore, I've got a bit lost. I wish there were different colours. That's looping all the way around, that's the same as looping around everything. What if I just loop around? So A3 doesn't seem to matter for what the transpositions do. Looping around here gives me, oh, that's doing, what's that doing? That's doing a swap? That's doing a 3 cycle. If I go around there. One of the roots is staying still and the other 3 are cycling around. Over here. Oh, the root's changing. It seems to matter. Oh my goodness. Okay, so moving in loops gives you different stuff. Yeah, okay. Pixel 3, non-trivial. Yeah, okay. Move the roots around and track what's happening to the coefficients. No one is second pass. Oh my goodness, okay, once we move the points to separate things. 3 roots permuted, 3 loops, each based at one of the eyes, which when we move the coefficients around them simultaneously induce the permutation 1, 2, induce any permutation of the roots we wish. Now form function space. Yep, sure, for cubics. Is there a degree thing on here that I've missed? Oh yeah. Oops. This is so weird. Okay, I'll do the degree 3. Moving around A1 doesn't seem to do anything. Moving around A2 isn't doing anything right now. Moving around both cycles them round. Okay. So the point of C3 corresponding to the coefficient. And here's separable, which I have in my notes as well. What's going on here? Denote the roots corresponding R1, R2, or 3. Jesus, this permutation. F3. Set of all function points in function space C3. Okay. More generally, zoom in a tiny bit. Sorry, it's really tiny, isn't it? There we go. More generally, set this to be points where it's separable, where you don't agree, where the roots don't overlap. A loop that, okay. A looping gamma which induces permutation 1, 2. Since it's non-trivial, there's a conclusion for proposition 1 up there. Oh, because continuous functions wouldn't behave like that. radicals in combination because nested radicals. Here we go. It's good, isn't it? I like the way it's kind of like the washing of the ocean or something. You get some control, everything changes, it moves and it forms. It's kind of like it's a living creature in a way that you're trying to understand the behaviour of. So this says I could do any cycle. Example of loop and see is image under square root is not a loop. Go around, and that's not how I choose that, even though some types of loops on whose image that I think is a loop. I feel like it's using more complex analysis kind of ideas than the Galois theory is. Dynamic gamma base inverse, the composite loop, go around and then back. More interesting version is the commutator. Do 1, 2, then reverse them, but do, yeah, okay. Trivial enough that their image under radicals is nice, but complicated enough. Oh gosh. Oh my goodness. That sounds really hard. Exists loop. Yeah, sorry, I late focus. Thanks for showing me this. Download. And that toy's lovely. But I think I want to go back to my attempts to do this using the general theory. Partly because well, I suppose my only way to justify using Galois theory now is going to have to be to do some other Galois theory. So let's get ready to do that. This has gone to sleep. So we're going to go in here, we're going to go here, we're going to go here, and here, and have fun. Over here I'm going to change this to be actually that, so that I can switch, turn off studio mode, and then yeah, I can switch between the two again. Okay, I can't actually see what I'm doing. Okay, standard notes. What do I want to do? What do I want to do then? So I could type in some details. Could type in some details, or I could put in or I could go and find out how Galois theory works for try and find a source for Galois theory on the kind of solving trisetting angles and stuff. Have I got anywhere else I could look for this sort of thing? Let's see if we can find some notes. As they say these days, finding the notes isn't the hard bit. Understanding the notes is the hard bit. So that link that I just got looked really exciting, but also a lot of complex analysis maybe. Not quite complex analysis, but just other stuff. Yeah, okay, here's some more Galois theory notes. This is probably good. No, I can't get them from there. What do I want? Can I get these ones? Not available. Course overview. Geometric problems. So why not? Do the notes have any geometric problems in? I think the Galois theory notes that I've got weirdly don't go into any of the stuff beyond there. Okay, let's try going past the Quintic. See what's beyond there for a fun bit at the end. So we did all this, special classes. We did the Quintic in here, solve for normal subgroups, which you don't need if they don't exist. Okay, is there anything else after the Quintic in these notes? I I think there's not. I've never really looked past, have I? That's fundamental theorem of algebra, which I'm going to read now, just for fun. Following well-known fact. P has a root in R of odd degree. Yeah, I believe that entirely. This is 0. We have, pull out the factor of x to the n. Since this thing, the limit tends to 1, there's a real number such that this is positive. I need to pay more attention, don't I? Since the limit of this tends to 1, eventually positive. Fine, okay. Maybe it's got loads of roots. Wait until it's done and settling down, and then find a point where this is positive. Similarly, there's a real number where this is negative. Maybe it's got loads of roots and then it's eventually negative. Wait, no. Eventually positive. What have you done? You've divided by x to the n. Why is there an extra bracket over here? I think it's another rogue bracket. Maybe I want to put both brackets in. Yeah, just why do I want to put both brackets in? Okay. So there is a real number such that that is 0. Similar to a real number there. On the other hand, this is negative positive, so p of x0 is negative and p of x1. Oh, when you multiply through. Cool. Oh, this is the thing about real polynomials. Great. Sort of sign change between minus infinity and infinity, more or less. Sort of. Right, here we go. Let's see, do I stand a chance of understanding this? We'll find out. P bar for this polynomial where you conjugated the coefficients. Yep, okay. I think if Q is P bar, then Q bar is Q, so Q is in real. Good, okay. Yeah, no, I believe this. Real coefficients. Bar twice, you get by twice started. Q bar is Q, so the coefficients match up. Fine, good. Oh, no. We need to show that P splits. This is going to be the proof that it's algebraically closed. Show that it splits in C. We can assume the degree of P is even and has coefficients in R. Because if this splits, we're done, because then C splits. Its roots are, is roots the same? Roots of the conjugation. P bar of, if P of x is 0, so for some particular x naught or something, then P bar of x naught is equal to 0 bar, which is 0. Okay, and bar is now complex conjugation. Okay, right, here we go. If R is splitting subfield, GB the Galois group of L over R, G2 and GB are two Silo subgroup. Gosh, how do we know that that's got degree, even degree? Off to a non-starter. In here, we know G's got an even degree. Two Silo subgroup. Size 2? Yeah, sure, okay. Oh, hang on, we know the dimension of P. So we know the degree of P divides, yep, the degree of P divides this. Take P divides the dimension of L over R. And the degree is even. Okay. Let M be C to the G2. The things in C that are fixed by G2. Bye, by the way. Take care. See ya. Have a good weekend. I'm just going to speed read it first. Fast and slow then fast. M over R is odd by the definition of Silo subgroups. Wait, what's a Silo subgroup? Was it 2 to the size 2 to the n? Yeah, size 2 to the n, where the rest of it's prime. So then the Tower law says that the remainder bit has odd. Yeah, okay. The quotient. So it's like quotient is like the leftover bit. Okay. What are we going to prove? We're going to prove that this is trivial, right? M over R is a non-trivial extension. Yeah, okay, and let alpha be something in M but not R. Then take the minimal polynomial, the degree divides that by the Tower law, in particular it's odd. So it's got a root. Okay. Contradicts the fact that alpha is not. Wait. Degree. The degree. M alpha is 1. The degree is 1. So it's crazy. A root in R, but it's irreducible, so that is the only root. Can't really have roots if you're irreducible. Root in the R, but irreducible. Odd degree. In other words, G2 is G. G is all of G. Yep. The size of G is 2 to the K. Right, so we're going to show that the size of G is actually 2, I think. Wait, this is going to be solvable. Oh, this is exciting. K positive. Where's P splits in R? There's nothing to prove. We're sort of done if P splits in R, because if P splits in R, then it definitely splits in C. Okay, proposition 513. The group is solvable. 513. Oh my goodness. Oh, it's size 2 to the K. Why is that relevant? What was 513? Not so familiar with that one. Oh yeah. Oh, this bit said it's solvable if it's P to the N. Because orbits stabilize the Lagrange orbits. There is something. Look at the center. Look at the center. Non-trivial center. Question by that. Induct. Center commutes. Normal subgroup. Look at the center. It might not be an abelian group, but the center is solvable. Oh yeah, it's actually solvable, so you can just go down to the identity from there. The quotient has a smaller, you're going to induct. Okay. Good. Back to the end. Down here, almost there. Group's solvable. Filtration, which has cyclic equations of order 2. Yeah, sure, it's got cyclic equations. It's got you can split it out into cyclic quotients. Right. Sequence of subfields. Yep, okay. Ooh, but then by the kind of converse of 5.6, the kind of thing about constructing roots, there exists a beta such that beta squared is real and L1 is formed by extending reals and betas. This is going to be C, isn't it? Any positive element of C has square root in R. You see that B squared is negative. Now compute. Comparing it with the square root of mod beta squared, because mod exists in the C world. Root L1, in particular x squared plus 1. So we're going to end up with C. Okay, no roots in R, and degree 2, L1 is splitting. Similar reasoning. Furthermore, L2 over L1 is non-trivial. Contradiction, because any element of L1, C, has a square root. You're fixed onto square roots, and that's all we're going to be doing. We're fixed for square roots now. Everything's got a square root. Ooh. Here's a square root. Okay, this one in particular P splits in C. That's really nice. I only wish that this carried on by doing some geometric stuff. So I'm going to try and find a different source for this application. This is lovely. I felt like I understood it as well, which is good. Maybe I'm getting better at Galois theory. C is closed. algebraically closed, that's what we say? Is that the phrase? Yeah, algebraically closed. Okay, so I want to find this kind of Galois theory. I'm hoping that if I just look at other lecture notes, so I love getting notes from the Oxford website, so I'm sort of hoping that I can just grab other lecture notes. Oh, I could do Balacendroy's notes. Only 32 pages, let's just skim it, let's go. Okay, let me see, let me just check what's in here. It's good to have a second source. Constructions, midpoints, yeah, okay. Balash, good stuff. Galois, Balash has come through. Right, I want to get these onto this device so that I can mark them up, which I'm going to do now. We're going to get some different notes on the screen that include a kind of fun application. We are going to do this by going to here and uploading, importing a file from my downloads. Just this thing. That's going to turn up in here, and then we can get it on here. I hope. Sync here. There we go. Right, new document. Landscape. There we go. Flip it around. Okay. So just for fun, we're going to look at Balacendroy's notes as well. So Balash was previously at Oxford. These notes are from a few years ago, and I picked them up because they're nice and short. We already know some Galois theory, and by reading another source, we get a chance to see things from a slightly different point of view, including some geometry stuff at the end. That is the plan. Okay, here we go. So there's two solutions to the polynomial with the symmetry of the situation. Solutions to generate a field extension. Okay. Degree 2. Okay, and you have put both of them in. Okay. K is a field automorphism defined by flipping them. Group, that's on that abstract group. Order 2, isomorphic to C2. Rational subfields, it's K fields by both of them. The main aim of this course is to study automorphisms. Special edge question with the general formula. Yeah, okay. Fini Galois. Okay, here we go. So some revision about rings and fields, worth looking at. Good. Integral domain, ring of integers, characteristic, definition of fields down here, 1.2. Field of fractions, A and B, such that, okay, field of fractions again. We've got to watch out for notation in this course, haven't we? Because it could be different. Like, I think this might be notation for an ideal that I skipped. Down here, yeah, this is ideals. Ideal notation. Triangle with a line under it as well, because it might be equal. Take that ideal. Can I have an objective? Okay, next up. Polynomial rings like this. If R's domain, R of X is a domain, because look at the top coefficient. Polynomial field of fractions of the polynomial, which we're using round brackets again. Okay, so just like the notes that we saw with Thiem and Rosler earlier this week. We have irreducible polynomials. You can't really split them up, factorize them. And it's reminding me, I do have to be careful about constant polynomials in sort of units. Prime like that, fine, okay. F is prime, even only if F is a prime ideal, yep, that for ring theory on one day. Euclidean domain, good. If there is, given F, there exist distinct roots, multiple disputes Mi and G without roots such that this, right, okay, take its roots out. Gauss lemma from rings and modules, iso-science criterion we've seen. Oh no, speed running this is great. Tricks and ingenuity is one of the things here as a way to detect whether things are irreducible. Is very nice. Group acts on here, considering the group acting on the ring, and that's a sub ring. Yep, okay, field. subfield containing the prime subfield K. Yep, good. And we're using this notation for the invariance fixed by G for all G. Okay, seems that might just be standard. I should get used to it. Good, okay, submarine test. And for a field K, to note this, the automorphism of all fields is bijective. All field automorphisms. Dupe field, that. So that's for all A and K, and look how clear this is. Literally fix. Literally fix. Fix K element wise. Okay, yep. Or over K. An action in the group G and a field K, it's group homomorphism. Faithful as the word for an injective homomorphism. Okay. And I worried a bit later, and when I was looking at the theorem, fundamental theorem of gamma theory, whether or not there was an injective or homomorphism. So maybe these notes will give me a different way to see it. Symmetric polynomials, good. Clearly of the ring. Yep, okay. Theorem following structure like that, uniquely expressible, and there's a way to do it. These notes can do the same thing. Yep, lexicographic ordering, here we go. Sum of squares is not elementary, but it does work discriminant like this. Oh, these notes are now following the same pattern entirely. Injection of fields. Oh, it's still defined equivalently a field inclusion. Fantastic. Not worrying too much about I of K or F of K here. Diagram form like that. Particularly for group G acts on M, MG, or M over MG. Okay, right, let's just say that. Okay. Tabular, good. FSA, irreducible. If A is algebraic, it's minimal polynomial, it's the unique monic polynomial, such fine. Then it has to be irreducible. Divides. If FA is 0, then M, the minimal polynomial, divides it. There's some Euclidean domain stuff going on there. Every algebraic extension is finite because, yeah, Q over Z is algebraic. Z's not a field. That's like 3 or 4 times now I've claimed that Z's a field. Q adjoin all the surds is all the surds, all the square roots of integers, non-square integers. That's a field, and it's algebraic, but it's not a finite extension. Okay, so the set of K generated by A, small subfield containing K and A. It's still annoying that it's kind of the same notation as field of fractions. It kind of behaves a bit like field of fractions, so that's all right, I suppose. Smallest subfield. Yep, okay, smallest subfield, we had that notation before. Containing K and S. Oh, surprising, that is a simple algebraic extension. We saw that one in the other notes. Okay, keep it moving, because we want to keep going and get on to homomorphisms, extensions. Why field homomorphisms? There is a homomorphism, the following properties. Restricted, does K alright? Alpha, beta, alpha goes to beta. Even only if M of alpha beta is 0, and roots go to roots. Okay, keep it moving. Examples. 2, can we send I? No, because there are no roots that we could send it to. Extend I to K root 2. No, so there's no kind of map between them. Okay. Field extension, yeah, that's very similar to what we've seen. Isomorphisms, good. From splitting fields, where you go where it all splits. Typically it's 2 split K, irreducible polynomials. Splitting field of this. Uniqueness in existence, you keep going, induct. This is the thing we saw before. Normal, whenever that it splits. That one doesn't. Same example. Sometimes the notes are kind of iterations of previous versions of notes, and sometimes there are just only a few good examples you can use for things. Characterization of normal extensions. Normal if and only in splitting field for some f. Ooh, that's good. We're talking about separable here for these Galois things? No. Okay, well, this sort of reminds me of the kind of map. Oh my goodness, look at that. Look at that. That's gorgeous. What's going on here? What is going on here? Find extension normal if and only if it's splitting field for some f. I'm just not that sure that I want to do that right now. Okay. Separable. They have distinct roots. Yeah, okay, all it has entirely different roots. Arbitrary polynomial is separable if all of its irreducible factors are. You see, there we go. There's the clincher, right? Any finite extension is separable. Double root. The derivative is 0. On the other hand, it's a polynomial. So do the division-y thing? Yeah, probably. Here it is. Consider that polynomial. Infinite field of characteristic P. Field of fractions. I think over T. And use those as your coefficients. Anyway. I'm over K is separable. How are we doing? It's after. Time flies. Page 12. Could go faster. Separable in the middle. Good. Yep. All fine. Stuff we've seen before. Presented in a slightly different way, so I should probably go through and read this at some point. Finite is separable. Yep. Okay. With that example. Zero primitive elements. Galois extensions. Ooh, with a nice diagram. Sigma I goes to minus I. Okay. Abstract group. Structure. Diagram. Very nice. One of those things not normal. Only the field automorphism takes minimal polynomial. So only one root. So a sigma gets fixed. The field extension is not normal. You haven't got enough roots. Didn't split over that field. Is that what normal meant? Okay. Different example. Yeah, okay, not all the several actually lines up with a bit of the notes that we saw as well. Alpha on K is the identity map on K. Good. By definition, fixed. Oh, this is good. The fixed field. Oh, calling this gamma of this. Or gal of the extension. I might say gal or the automorphism group of. Yeah, KL. Okay, so this gamma group thing. Contains K, but there's no reason why that should be equal. Okay, yeah. Galois extension if it is. So I think this really highlights the kind of way that it might not be K, but could be for a Galois extension. Say the extension is Galois. Okay. Splitting fields don't have to be Galois. Finite group order, technical core of our proof of fundamental theorem. Linear independence of field homomorphisms. Oh, this is the characters thing. Degree of a fixed subfield. Affects transitively, that's the number of elements of G. What does that mean? Find a group acts faithfully on the field L. Besides the field O, feels a bit like the Martin's lemma thing about counting degree of a fixed subfield. Yeah, to do with the group, subgroup of automorphisms that's acting on it. Okay. Yeah, linear independent stuff. Main theorem. Inclusion reversing correspondence. Inclusion reversing, I love that. Screws are given by this. Like these a lot. Gamma subgroup. Let's clear this. We have this. On the other hand, this. What's this inclusion reversing? We need 2. We need a lemma. It's 2. Gal white if and only if this thing. What's your lemma? Ooh, stabilizer of a translator, the conjugate of the stabilizer. Ooh, this looks exciting. I want this. This might be a better way to do the thing that I need in the shortest route. Okay, read the proof at some point. Particularly normal. Then you get this normal subgroup. Subgroup, here's this thing. 1-to-1 correspondence in 1. Slightly more words, or maybe I just understand it now. I've seen some other words. We assume the character of code 0, separable Galois, Galois groups polynomials, go. So it's going to look at the discriminant, and it's going to tell me maybe this is part of, yep, the squares alternating group thing. Okay, there's an analogue to this in the notes that we read. Just checking I'm not missing anything. Wow, look at that. Oh, it's supposed to go up to the L, I think. Not just wider brackets. The diagrams in this are become more cool. Being typeset with slashes, which looks quite laborious, but I guess drawing this with ticks would be extremely weird. Or just hard to do. Cubic polynomials, let's go. Quadric polynomials. Oh, here, like the solution to the quadratic. Yep. In which case it's this, which we saw before, S2. S0 A3 depending on the discriminant, and that's all fine. X cubed minus 2, and we're going to solve it apparently. Let's go. Right, omega. Okay. Quartic polynomials. Okay, splitting field is LF cubed alpha I. 2, count the same. Degrees clearly most 2. There is an automorphism. Fixing QI mapping alpha to I alpha. Fixing QI. Oh, fixing Q. Oh gosh. Spinning around the alphas. Dihedral group. Ooh, okay. And then cyclotomic groups. Primitive things. The units of Zn. Yep. Abelian subgroup of the okay thing. Result of this. Cool, okay. In fact, the cyclotomic polynomial is irreducible for all n. It's very easy to see for P if P prime won't need it. Oh, okay, good. Also using n equals P prime. Often reducible over finite fields. Okay. Extensions like this under this assumption that the characteristic is not n. Assuming that that root already splits, then you see all of this. And extension, injection map, homomorphism. Yep, okay. We talked about this yesterday and it was fine enough, I think. So I don't want to read the proof here. Cubic square radicals, off you go. There's the beta cubed and gamma cubed with the depressed cubic thing in there as well. Solvable groups, also known as soluble, I see. Hi, if you've just joined us, we are speed reading through some Galois theory notes, trying to get up to using some Galois theory to do some, well, we've thought about the solutions to the Quintics. We were on a quest for the Quintic. Now I'm maybe going to try and think about some geometry stuff. We just want to see it at the end. There is some stuff about normal subgroups down here, which we saw earlier in the week. Solid by radicals, which is these cover extensions. And there's going to be a thing in here about, yeah, these betas. Okay. Should be a thing in here about throwing in the roots of unity. right? What's epsilon? Yep, it's a root of unity. Throw it in. Splitting extension, solvable, and say the subgroup is solvable. Tower feels like this, and you're going to move down over here, right? Reduction, the radical extension M of K. I do like that. Like this. The place where L is fixed. Oh, I don't know what's going on. L is contained in M, and radical extension H. Where's 4? There you go. We're going to do an example of insoluble quintics. Yeah. Ooh. Isomorphic to Sn, like it's always Sn. N to be the 5, letter K is not contained in the array. Which quintic? Oh, it's the same quintic down there. The one that we've been looking at all week. So that's good. There we go. Quintic. Then there's some stuff about finite fields. How much do I want to know this? How many pages have we got left? We've got finite fields. Just going to characterize the splitting things to do with. Ooh. Finite fields. Finite extension of finite fields. Separable. Geometric instructions. Okay, here we go. Basic operations. So we've got this page, with 30, 31, and some stuff. And then algebraic closure is this, which we just read in the other ones. One of the least understood and most mysterious objects in mathematics. The closure of Q over Q. And the Galois group of that. Wow. Description of the Galois group of the closure. In increasing order of difficulty. Oh, these notes are fun, aren't they? ACT. FP is a unique limit. Oh my goodness. Kind of a limit of the finite group. That's mad. Nobody knows. Amazing stuff. Right, okay, so I just want to do about 2 pages here. Gauss, it is possible to construct a 17 gon. Sounds brilliant. Can't trisect. What are the other things? Let's read, let's just read, so, fast, slow, fast. We've got 2 pages to understand here, and like 2 hours, so we're going to be fine. Decide whether it goes in the notes or not. Given 2 points connected by a line, given a point in our square on a line segment or a circle, given any pair of lines or circles with points of intersection. I thought there was some stuff about taking a line of a given length and moving it around. Constructing regular polygons. Points of intersection. Maybe you don't need that. Given finite sets of points in R squared, we say that S can be constructed from S0 if there is a chain of subsets. So we have to be given some points to start with, such that the points in SI quotient SI minus 1. No, without. That's really without. Having constructed from points in SI minus 1 using the basic operations. Start with 2 points. We say that that distance is 1. So we're going to be interested in the distances we can form. For example, can you make square root pi or something? Okay. Some basic constructions. Find the midpoint. I remember doing this at school. Put a line through them. P0, P1. Put a line through them. Take the intersections of 2 circles using the line segment as its radius. Okay, so there's no moving around. Take the intersection. So the 2 intersections, gosh. So it'll leave 2 more points in the intersection of this new line. with the original line segment is the midpoint. Okay. Yep. Given T1, T2, T3, I just can't see the. This is stupid, but I can't see the field, let alone the automorphisms. We're going to get there in about half a page, so let's go. Given P, Q, and R, we can construct T1, T2, T3. So given P, Q, R, we can construct T1 and T2 and T3 so that for the length of the segments, PQ times PR is PT1, the length of PT1. We can find a point somewhere with products. We can find a point such that PT3. Oh, we do square root. How do we do that? Sounds fun. Take square roots by doing this. These constructions are great. Multiply lengths. I don't know how to do any of these. Fun. Okay. Also, add and subtract segments easily. Yeah, sure, okay. Using circles or something. Given a set, S is just some points. Let KS be the rationals extended with. Oh, here's the field. The rationals extended with the union of I of those points, but that's of both xi and yi. So Q and all the xi and all yi extend overall. So y and I, ks. Start with ks0 is q. So s0 you can add, multiply. Oh, add, multiply, and divide. But you can also do square roots. If S is constructible from S0, then there's the field. Throw in the numbers, the lengths that you can make. Apparently there's ruler and straight edge ways to do field stuff like adding, multiplying, dividing, and subtracting. And also square roots. The action of doing the square roots feels like a, oh hang on, the action of doing square roots is going to be the thing that gives all these twos, isn't it? It's not obviously that you can't do anything else, but those are basic. These are examples. Sorry, not the So understanding these is kind of separate. Down here is where we would like to actually show these into order 2 as the extensions. All the extensions that come from quadratics. Okay, so when you extend, you already had all the xi's and the yi's. Okay, and it's going to be something like each time you do an operation, it depends on the previous points in some sort of quadratic way. I think I've heard that it's all coordinate geometry is all quadratic stuff. Okay, let's go. All points of point are solutions of quadratic equations. Here it is, quadratic equations carved into KS. This is true since, here we go, computing the intersection point of two lines is a linear problem. You gave me all the points and you asked me to do a linear construction. Yeah, okay. What was the second part, sorry? Down here? Any point with P and point P with coordinates now. Okay, you make anything. Okay. Computing the intersection is a quadratic problem. Computing the intersection point of two circles is a quadratic problem. Yeah, I guess I want to write out those problems. So I've got like exclamation mark, write out these problems. To argue by induction on n. If n is 0, points with q coordinates are constructible. Since that means 2 for any alpha and ln solves a quadratic polynomial over ln. Using these constructions perfectly solve quadratic geometrically. Following group theoretic claim. chain for any group with two n elements. That's the structure theorem on structure theorem combines maybe with there's an element of order 2 Cauchy or something. This extension is Galois. We're reading this fast, then slow, then fast. Not possible to divide general angle into 3 parts, and it is possible to construct a regular 17 gon. Here's a single angle which we can't divide. Suppose that's constructible, which is the root of a cubic. Geometric construction of cos pi by 9. Geometric construction of alpha. So, but the cubic is irreducible over Q and has degree 3. So it's not just solvable here that we argue about for these geometric constructions. We're arguing about all the field extensions have degree 2. Any extension of Q at degree 2 to the n. Tower law. Bracket. Clearly constructing a 17 gon is equivalent to constructing this. Let this be that, and we get the tower. 17 is 4 squared plus 1. We get the tower. What? So you make Q. Oh, here's the tower. So these are the subgroups, and these are the things you've extracted. That one as a quadratic from here. This one as what is going on here? 17 is 4 squared plus 1. Q of cos is Galois over Q with Galois group C8. Do I believe that? Galois group C8. So there is some 8th degree polynomial, is that what you're saying? 8th roots somehow. Yeah, no, okay, that's exciting. Psi plus psi inverse. Yeah, so you're getting there by a degree 2 thing. 4 squared plus 1. So the extension of this thing over here, that's a root of x to the 17 minus 1, but with minimal polynomial, min polynomial deg 16, because it's not 1. 17's prime. So if you've got a prime that's 1 more than a power of 2, is that what a Fermat prime is, more or less? It'd be nice to say at the end, or more than that. Fermat primes are 2 to the n plus 1. Be nice to get those in here at the end. The ones you can construct. Okay. By our theorem, that's constructible. Should be 16. Oh, just throwing this in would be cyclic because that's a roots of unity kind of thing. So that overall is C16, and this thing in here is C2, but the quotient there is C8. C16 quotient C2. You have to say which C2 you're quotienting with, right? C16's got loads of C2s. Do you have to say which C2 you're quotienting with? It's tricky. You've got to look at the normal subgroups, I think. Anyway, there we go. So I think is constructible. But there's sometimes you can't construct these. What do you need then? So sometimes this subgroup, right, so there's some structure stuff in there about whether that group is cyclic or not, or whether it's made of. We can do C8, chain of subgroups, finite group of 2 to the n elements, chain of subgroups such that each one has size 2. Okay, okay. We've got some stuff to understand here, but it does look pretty nice. These quadratic problems mean that each step you're doing a degree 2 extension, so overall your Galois group must have size 2 to the n. Trisecting an angle will be degree 3. Galois group's really straightforward if you do straight line stuff. Huh. But then you want to make a pentagon, so I think instead try and read along with a pentagon. And it is, by the way, kind of cool that you can make a pentagon, but you can't solve a quintic. 5 lucky number in one sense, unlucky number in a different sense. I think this has got to go in the notes. Yeah, cool. Okay, coming up to 3 o'clock, we've got some cool stuff here. I'm going to take a quick break to get another hot drink, and I'll see you back in a couple of minutes. What are we doing? Yes, that's what we're doing. Quest is to be continued. Okay, we've got just a little bit to do here to wrap up. I'm not sure if I'm going to make it to 5 o'clock. I guess I probably should. It is Friday. It's been really useful chat. Thanks Twitch. From people popping in just to check out what I'm doing, to people giving me advice and notes and teaching people maths. I've enjoyed that a lot. Right. Gonna think about pentagons. Am I quite like this? I don't love it. I kind of want to see, what's the easiest proof that pi isn't algebraic? I don't actually know a proof that pi is irrational off the top of my head. Proof that easy. Oh my goodness. Wikipedia says, in 1882, Ferdinand von Lindemann published the first complete proof of the transcendence of pi. He first proved that e to the a is transcendental. E to the a is transcendental if a is a non-zero algebraic number. E to the a transcendental. He proved that all of these are transcendental if a is non-zero. If a is a non-zero algebraic number. Algebraic here means that it can be written as the root of a polynomial, and then brilliantly we know that e to the I pi is -1, which is not transcendental. So this is not algebraic. I pi is transcendental. Since I is algebraic, pi is transcendental. There's a bit in there. Can we learn the Lindemann-Weierstrass theorem off Wikipedia? Just a proof on Wikipedia. Ooh. So it's completely different and very hard. Number theory another time. Pi is transcendental. So this is the thing about squaring a circle. Oh my goodness. Is there a shortcut or to just do pi? Letter B also suffices. Oh my goodness. So Wikipedia's got a load of stuff. Oh, which looks a bit like the characters we were doing. Let me show you it quickly. How do I find it? So I'm going to go to Lindemann-Weierstrass theorem on Wikipedia, just to show you some cool maths. There's this thing I've just seen. So I was scrolling through this Wikipedia page, which is really complicated, and like Wikipedia pages sometimes are. But halfway down to this lemma, if these things are integers and these ones are distinct algebraic numbers, then this combination is 0 only if all the b's are 0. B subscript here. This reminds me of the. What does it remind me of? It reminds me of the characters thing we saw about homomorphisms from a group into a. Homomorphisms from a group into the units for field. Here, the group is. Oh, it's not a homomorphism, right? It's not a homomorphism. E to the gamma. Yeah, I think it's not that. Similar vector combination. Loads of stuff going on. Lemma B is enough without this final step. Plugging in I pi and 0 or something. Gorgeous. Oh my goodness. I'm never going to understand this. No, that's not the right attitude. I could understand this. Just maybe not right now. Okay. Back to the notes. What have we got? We've got some cool stuff at the end here about constructing things. Ooh, what was that? A. A. Ooh, look, black bold A. It satisfies some polynomial equation of Q. Ooh, problem sheet 1. Yeah, let's read this stuff about extensions because it goes somewhere weird at the end. Closure of Q over is. Okay. Fundamental theorem of algebra R. The closure of R is C. This is the union. So closure of the finite field. Where do you go if you want to solve all polynomials with coefficients from modular arithmetic. It's the union of those inclusions. Oh gosh, because of the prime powers thing. So, do you want the closures here? Compare elements. It's really a limit construction, oh gosh. No, it's the union of all of these apparently. Oh yeah, here's this comment at the end about Norrie or something. Okay, fine, there's not really much for me to understand here, is there? Because I can't do that question. Okay, I'm looking out into the wide world of stuff that's beyond what we've done to get to the Quintic. I think, rather than boring anyone by typing up some notes, but it's good for me, isn't it? It's good for me. Forces me to stay on task. Why are we going to come back to this? That's what I said to Anders earlier. What if I never come back? What if I never come back? There's a kernel in there. Normal subgroup. Okay, I think I'm running out of ideas. Then we might finally be exhausting the quest for the Quintic to the extent that I feel kind of happy and don't want to type out all of the details on a live stream. I'm too self-conscious even for my typing. So I think that means, with a look at the map, I think our quest might be coming to a close, sort of wrapping up. We've got this kind of minimal route through the theory about doing nth roots not being that exciting in terms of the Galois group structure, permuting the roots only by multiplication if you respect roots of unity, and you might as well, that is still solvable. S5 being a complicated group, we should probably dig into that a bit more. Yeah, okay, I guess it's come to this. I've got a bit of time on the clock, and there's one big thing that I don't understand at all. Not that, not these. Oh, although I should look at this. Oh gosh, stars for key things, I think. And that is the proof of Arthur's lemma. So we decided we didn't need this for our shortest route. And we did go back and understand their orbits a bit better, but it's the proof of Arsen's lemma. So I think I need to jump in just so that I know that I understand it. It's going to be a little bit of hard work, I think, but that's good for me. Okay, we're going back in for one last voyage through Galois theory to try and make sure that I've properly understood. Oh my goodness, proof of Arsen's lemma, which is down here. Statement about fixing fields, and there's a complicated looping kind of subscript superscript thing going on, and to do with matrices, and it's got an exclamation mark. Right. Okay. Lemma first. So I'm going to try and get rid of the scribbles on it as well. There's loads of scribbles up there. So there's a lemma first. K be a field, and let G be a finite subgroup of the automorphisms that maybe fix K and maybe don't. Find the stuff that they fix. Find the stuff in K that is fixed by G. Oh, so it probably doesn't fix K. K is the big field in this case. The dimension of the Galois extension. No, the dimension of the 3 PM on a Friday. The dimension of K over Kg is less than or equal to the size of G. Okay, so not too big for the extension. k over the fix is not that big. Not that big. Not as big as the size of G, right? So be greedy, right? If G fixes lots of stuff, no. So G's quite large. If G's quite small, this is saying, oh, there's not much space for k over kg. Stuff fixed by k must be almost as large as k, in the way that we're talking about dimension for the size of these fields. Everything's infinite and many dimensions. Okay. Enough abstract waffle. Let's go. Suppose not. Then there's a sequence of elements of k, the large dimension of k, linearly dependent over this, using that as our kind of scalar thing down there, linearly dependent over things that are fixed by G. So if G were to come along, that automorphism would fix all of the things in kg, it would fix all the coefficients in this linear independence. Okay, probably important. And there's loads of them. This number of them is bigger than the size of G. Let n be the size of G. Okay, we start calling that n. And let these be an enumeration of the elements of G. So you've got all the elements of G. They're not called gamma here, they're called sigma. They're from G and they're called sigma. We can do this. We've got a matrix. Matrix looks like this. It's the images of all of those points now. D elements. The columns are linearly dependent over K. Should be KG? No. Over K. Columns of this matrix are linearly dependent. Oh, that's just it's the shape, right? Because of matrix. Matrix is a wide matrix. So algebra on K. Come and do your algebra and sort of rearrange it and do some row elimination or something, and you get some dependence. Fine. I guess column anyway, do some elimination. Okay, wide matrix. So there exists a sequence where at least one. Yeah, I guess as a matrix you could talk about I suppose the columns spanned. The span of the rows and the span of the columns or something. Been a while since vector space theory. Good times. Okay. Exists a sequence where at least one BI does not vanish. So you could do this. Now the BI are in K, but not necessarily KG. Ooh, if you've just joined us, we are trying to understand the proof of one of the hard bits of the lecture notes. A proof that I've skipped 2 or 3 times on the way through, but we're going for it. Now I've got to remember, these elements are supposed to be a kind of basis, I think, for K, or at least, yeah, or have maybe not a basis for K, but are linearly independent. I might as well extend it up to a basis, but hey, never mind. And we've now got a sequence where these columns vanish, where sigma n is all the things in the subset of the Galois group. We've got a subset of our automorphisms, which is shuffling around the elements relative to the stuff that's fixed. I'll try and look at the dimension. So G, the things in G stir around K, some stuff's fixed by all of them. What's the dimension for the leftover stuff? Okay, let's do that. Choose a sequence such that number of non-zero elements is minimal. Fewest non-zero elements. Suppose that the first one's a non-zero and the last one's R0. quantity R. Divided by BR. This is a combination that's 0, right? This is a combination that's 0. So it's got some terms in it that are non-zero. We're going to do some elimination. We're going to do some subtraction. By the assumption that they're linearly independent, these alpha that exist. Oh, we can see we go. It's supposed to be linearly independent over kg. There exists some I naughts in the first bit, such that these things are not in kg. Because if they're all in kg, if all of these betas were in kg, then we'd have something like this. We'd have beta sigma alpha 1, something like this, because there's some reordering going on, which I'm not too worried about, but there's something like this, plus beta r sigma alpha r. This is the kind of sum that we're looking at. So down here we've got sigma k. At least one beta I does not vanish, such that. What's k? Such that for all k. So 0 for all k. Now, if all the betas were in kg, they would all be fixed by sigma. So sigma k for all k. I don't know what I mean for all sigma. If yeah, okay. So we would be able to bring out the sigma from all of these terms and mash it all together, and we get sigma of some stuff is equal to 0. If all in kg, then we would get sigma of stuff, but sigma's an automorphism that only sends 0 to 0. So contradiction, because we'd have a linear combination that's 0, and those alpha i's were supposed to be linearly independent. Good, okay. Oof. Renumbering again. So, okay, pick me one that's not in kg. Everything's fixed by g. Sort of some interesting action. Right, we're going to act on this, aren't we? Yeah, we're going to apply this. Apply something where it's not in the fix, so there's something that moves it. Apply it, go for it, and we'll get this over here. This thing is nice to what's going on here. That's the same. These permutations. Why is this nice? In other words, sigma k naught. This is an automorphism of the group, and such that. Why is this one gone away? And tell me about alpha I? The alpha i's in the. Where are the alpha i's? What were the alphas? They were just points in K that kind of formed a basis, more or less, I think. So why is that? Oh, is this a group thing? Is this a group thing? To say you've summed over. Oh no, maybe not. I was thinking about summing over all the sigmas. That's not quite what's going on, is it? Yeah, I don't get that step. I don't get where the sigma k naught has gone. Applying that to all the equations. Oh, this is true for all k. Oh, okay, so this is true kind of for all sigma k. So that's kind of just renumbered. This thing is some coefficients at the front, but then for each one, it's been. So for all k kind of means for all sigma. Okay. It's true for all k. The sum goes over the i's, but it's true for all k over here. to n. So the tricky thing is that then that's the same thing as doing the sum looking at all of these sigma k's. We've got the same coefficients in there, but instead of looking at the coefficients kind of fixed each time. Has nothing to do with k. That's nothing to do with k, which says for all k, this is the case. So okay. So this goes over between them. This sigma thing, this kind of group theory thing, is that if you're going over all sigmas, forget these numbers for now. If you're going over all sigmas, then special thing multiplied by that. The action of the group on itself just permutes the group's elements. So it's the same thing as looking over all the sigmas. Still not totally happy. You can have a look down here instead. Sigma n is an enumeration of all the elements. Slightly funny to me to have all of those like that. Oh well, okay. What is this? For all k means that combination, you fix the betas and you do this combination of the vectors, which means that the combination of the vectors means that it's 0 for all k. You get the 0 vector. Okay. Subtracting the equations, we obtain this, where this thing is non-zero at the front. Beta r is 1. Equivalent to writing, you can sum up to r minus 1, since this is not equal to beta I. Why have we said that's not disappeared? Which one's gone? Yeah, I think one of the terms is cancelled, right? We've now got r minus 1 terms instead of r terms. Okay, fair enough. Which term's gone? I can sort of still see the beta 1 term. Wouldn't it be fun if that was equal? Oh, this is a non-trivial combination. It's got fewer terms. Beta r is equal to 1. We made the last one. Unity. So that sigma, because sigma tends 1 to 1 as group automorphism, and 1 is in k. G, definitely fixed by all automorphisms. Oh my goodness, right, okay. So there's some matrix stuff in here to do with the kind of tracking the dimension. It says if you've got some group elements but then loads of vectors in the associated extension over the things that are fixed by all those group elements, then consider a sum of those, that they're linearly dependent because there's more columns than there are rows. That's a bit suspicious. That means that you've got some combination of these vectors, which is 0 vector, 0 for all elements of the group. Once you've got a combination that's 0 over all elements of the group, you can start doing tricks with it, where you do things like applying this again. I said the coefficients are not all in there. It's a weird trick to say the coefficients are not all in there. Yeah, it's like saying they're not all 0 and not all fixed. It's kind of the same. They're not non-trivial in a way. And then the combination together means that you end up with something like this. I'll do some clever subtraction. BR is 1. So we've seen this before actually. We make one of the terms cancel and we make sure a different term is non-zero. I've seen that somewhere else. To achieve kind of two things at once, to make sure that we cancel something but not everything. Yeah, okay, so we've seen that trick a few times now, to reduce the number of terms working down. Okay. Cancel something but not everything. Yeah, pretty good. Okay. And then that's the proof that it's not too big. And then there's a tiny bit of proof here, which involves one of those subscript superscript things. So I think I should spend 10-20 minutes now on, oh my goodness, one of those points in the show where I've got about 4 lines to understand and it's going to take me forever. Because look at this. I mean, look at this. I'm going to have to understand, oh gosh, both ways round to prove that these are equal. It's like an if and only if thing where also one of the sides is extremely complicated. Superscript, subscript, superscript. Okay, we can do this. So both sides are by definition, so whichever side you think is more obvious, don't pick a direction, pick an obvious fact and then try and work out which side that is. I think it's more obvious that G is a subgroup of these automorphisms. That's what G, oh gosh. No, change my mind. G, oh gosh, so if I believe that G is a subgroup, then the fix here is larger. On the right hand side, oh gosh, we've definitely had this sort of argument before. On the right hand side, this is the things bar for entry here. So you have to be fixed. You have to be in K and fixed. This notation, the superscript, means it's fixed by everything up here. So automorphism of K over KG. Those are the automorphisms of K that fix precisely KG. So the bar here, oh gosh, just understanding this is so annoyingly hard. So KG is things in K. This is literally, well, I've written that out, it's literally this. Okay. No, I like that actually. KG, like this, means the things in K fixed by G. What's G? It's a subgroup of some automorphisms. So G is in the group of automorphisms which fix K by definition. So not very exciting observation, but K is in KG. They had to fix K. No, what's G in? I've put so many K's and G's in the wrong places. They don't have to fix K. Automorphisms. The G things are just automorphisms. G automorphism of just as rings, not worrying about fixing anything of K. That's right, isn't it? Definition over here, or explanation of what these things are. Oh, I've scribbled all over it. G subgroup of automorphism rings of K. Okay. So, 20 minutes, 4 lines. Let's try and understand the automorphisms that fix things in K, that fix that set. So this is things in K fixed by everything in G, fixed by everything in G. All in G, all gamma in G or something. So, this stuff is fixed by all gamma in G. And these automorphisms are things that fix. These are, these fix precisely KG, maybe some other stuff as well actually, because they might not be Galois. But these fix everything in KG. What was KG? It was things fixed by all the gamma in G. So these things, because they're fixing KG, so they fix. So these things fix all things. So fix all the things in K that are fixed by all gamma in G. That's quite a convoluted statement. So I've got some automorphisms here. What do they fix? Well, they fix everything in K which would be fixed by everything in G. Crikey, you say, that's impressive. Your automorphisms fix. Is that impressive? Isn't that impressive? You've worded that very precisely. You're fixing all the things in K that are fixed by everything in G. So I mean, that includes K. So this is definitely I'll give you that. That's definitely a subgroup of G. No, G definitely does this. Yeah. I can't get it the right way around. You've got to also get everything the right way around, all the way around. I'm not even down to this. I've got to get down to here. Maybe I'll take this as definitions. So exclamation mark on this. Really struggling to piece this together. And then those things turn out to be equal. Actually, let's put my exclamation mark out to here. And then I guess there's a lemma to say that that was actually a finite extension. Not too big. Conclude from theorem 3.18 is at most as large as the size of a group. Conclude from 3.18. Finite extension. Do we get any other facts about K? We get no other facts about K. I have scribbled on Arthur's lemma quite a lot. We get no other facts about K. So how could 3.18 tell us anything? Since it's a finite extension, conclude from 3.18 that it's a splitting extension of a separable polynomial with coefficients of kg. So there's an automorphism group, counting it for kind of Galois setting. 3.18, but that was the separate definitions thing. If it only fixes the identity, right? Right. So if this says Galois, right? This means Galois, I think. The things fixed by this automorphism group is precisely. Maybe if I wrote it out with K's and L's or something, then I would have noted that this is the definition of a Galois thing. So it's why does it matter that it's finite? Finite extension. Why do we need finite to do 3.18? Down here. Oh, we use that in the statement of 3.18. Right, okay. 3.18 needed a finite extension. I didn't spot that previously, might go back and look at it. Okay. So down here, conclude that everything's sort of a Galois extension. On the other hand, I'm jumping the gun again because there's Galois down here. I suppose I know at this point that it's Galois, but I don't know the size. But then I can conclude the size from this argument. 3.17 looks at the split here, the number of automorphisms looks like this group. Other hand, 4.3. Oh, we just said it's not too big. So this automorphism group is at most the size of G, but G is a subset of this. So it's one of the confusing statements up here. So the size of G is at most, no, normal subgroup, and therefore they're equal. Yeah, normal. So size is equal. The size of G is large, and it's a subgroup, so it's equal to the whole thing. So now you know that. Now you know that the Galois group for K over Kg precisely is G. Up here we knew it was Galois, we didn't know the group. Down here we know from the size of the kind of automorphism thing. Now we know it's Galois group G. Okay, so we can do half the conclusion and then the other half of the conclusion. Okay, so I should probably understand these automorphisms together, but I've got a feeling that it's just a funny string of set theory stuff, backwards and forwards, and nothing to do with Galois theory. Well, maybe, I mean, there's loads of automorphisms around. Oh, should I rewrite it? That might be fun. Yeah, let's try rewriting it. It's worth a try. So, if I relabel K to be called L, and oh my goodness, so my version of this statement is going to be in my notes somewhere. KG, K to the or, okay. So we have my version of this says something like given L a field and H a subgroup of automorphisms as rings of L, let K be the things in L that are fixed by H. Now, here's what we're trying to prove. We're trying to prove that KG, so for Arten, that's big group, things that are fixed in the big group by the subgroup. For me, that's just called L. No, it's just called K. And on the right, L, and this is the very natural or KL. So things that are fixed, show that. And then I want K is equal to the things in L that are fixed by the automorphisms KL, which means it's Galois. L over K is Galois, i.e. L over K Galois. Do I actually mean K? Sort of. Yeah, sort of. I'm not worrying about inclusion stuff. Oh, definitely not here. Okay, so different notation over here, but that's kind of the spirit of what we're trying to do. And now we go. So, H is a subgroup. Oh, low battery. Because it wasn't plugged in. The thing about charging cables is you've got to plug them in at both ends. There we go. One day we'll have a charging cable you only plug in at one end. That's kind of beautiful, really, isn't it? H is a subgroup of that. Let's write it out more neatly in case I need to see it later. Roots of L. KB, things in L that are fixed by H. That's lovely. And it's going to go two ways to show that each side is inside the other. So it's going to be like show that K is inside things of L fixed by K, and the other way around is to show that L or K, L like that. Show both ways around, the conclusion being that they're equal. Okay, so in words, what does this mean? This says that K is part of the set, part of the subset of L, subfield I guess, but part of the subset of L fixed by, and then up there is the automorphisms of K of L. So dot dot dot, the thing upstairs is or KL. Oh, K definitely is part of that subset because or KL definitely fixes K. Yeah, so these automorphisms all have to fix K. They all fix K. So this set definitely includes K as something that's fixed. Okay, maybe the other way around is harder. Say that L, things in L. Yeah, it's quite tempting to try and reverse that, but I think I need to think of something different the other direction. Intersection. It's tempting to think about like all of the automorphisms. If they fix some other stuff, do they just fix K? The fix is precisely K, right? Oh, that's a Galois. That's Galois once again. Worried that the fix is precisely K, but that's what we're trying to prove. Keep remembering this line from the definition of a Galois extension. I'm thinking, oh, that's true, isn't it? And it's not true in general. So we haven't yet used the fact that K is L to the H. So here we're going to use the fact that K equals L to the H, with H a subgroup of the automorphisms. So want to show that L to the H has subset things fixed by all automorphisms. I mean, that's just going to be because if you're fixed by all the automorphisms, then you're certainly fixed by all of these automorphisms in H. So this just follows, I think. So that way around we've used the fact that K is L to the H, and the other way around we've used the fact about what automorphisms fixing K. One way around looking at these automorphisms, and one way around looking at the definition of precisely picking up K. Okay, I think I've now got to the point where both of those, I'm happy with both of those directions. Not certain I could recreate this, but think about it carefully enough that I was saying different things, and thus likely to be both directions in some order. Okay. Good. Okay. I'm going to get rid of that inane scribbling over there, and I think declare myself pretty much done for the day. Clocking off at 20 to 4. Yeah, I think so. We've seen a lot of theory today. I think we've now got a good understanding. I'm not going to do the typing up live on stream. It's too clattery and it's too exposing for my terrible typing speed and accuracy. Right, okay. One last look at the map. It's been a fun journey. 12 pages of notes, wow. Including some snappy notes about ring theory up there. Oh no, I remembered. Rings. Classification of revealing groups. Modules. I want to know all of it. I've remembered some more stuff I want to learn. I'm going to stay live. Learn more things. Right, okay. We're parking Galois theory, so let's do the wrap up for Galois theory. There was a lot of this. Rings, lovely. Root of least resistance, which I'm now quite happy with. So, hello Ashwinder. I'm just wrapping up the Galois theory. Then I'm going to go and learn something different. So I'm going to talk myself through it one last time. I feel sad in a way. It's been all week. Well, here we are. Okay. We went on a quest to find the Quintic, to understand why the Quintic doesn't have solutions, but more importantly, the real quest was the Quintic we made along the way. Actually, you're the second person today to ask me for my favourite number. I can only assume this is some sort of running joke or something. I like 37. It's a hexagonal number. And later I found out that Sheldon from the Big Bang Theory also likes 37, and that made it a bit worse for me, because I try to distinguish myself from, try not to get confused for Sheldon from the Big Bang Theory. 37 is just quite nice. It's prime. Anyway, I see that I'm converging. Good. Okay. Wrapping it up then. We avoided a lot of the group theory and the modules. And we spent a lot of today just going for the quickest route to the Quintic and back again. But the real quest, the real Quintic was the Galois theory we learned along the way? No, not quite that. The real quest was the Galois theory we learned along the way. Got this idea of, in particular, fields containing fields behaving like vector spaces. Something I didn't really know at all, right? Yeah, I didn't know that before going into all of this. And the way that those permutations preserve roots is pretty good. Okay. We're going to do a quick excursion. We've had a quick look at some other roots, but I think I want to go and look at the classification of simple finite groups, of abelian groups at least, which is in the rings notes over here. How quickly can I learn modules? Well, 23 is good. That's the racing number for Alex Albon, who's a driver for Williams. Why do you like 23? Here we go. Oh gosh, about 20 pages of this. Scalars from a ring rather than a field. Okay. So you can't build this field of fraction stuff. Pi's good. There's this number that's really large that is something to do with permutation theory that I should learn it, because then I can, when people ask me for my favourite number, it would be an excuse to then talk about this permutation thing, double derangements number. But the number's really large and I can't remember it, so I can't really say it's my favourite number. I just can't remember what it is. It's pretty embarrassing for your favourite number. Whew. Okay. So you take a Euclidean domain. I would like to imagine Z. Oh, no, that's coming up in a moment. You take a Euclidean domain, fine, I'll imagine polynomials or something. Abelian group together with scalar multiplication by elements from R. Why is that like a vector space? Why is the Rm such that it behaves nicely, distributive, and obeys the ring addition and ring multiplication. Z module. Oh, where it's defined like addition. So if you think of it as addition in your group. So you've got a group M and you're allowed to do R things to it. Okay. R and Euclidean domain. This is one of the ones with loads of properties, right? A module over a field is a vector space, because then you can do combinations. These are your scalars, and you can add things together because that's a group, and you can multiply by things from the field. Okay, good. Hi, if you've just joined us, we're doing a little push past ring theory. I decided I wrapped up gamma theory for the week, and we're doing a push to try and understand modules, which is a new structure, a new sort of object, not mentioned so far. The advantage is that if we push through 20 pages of notes, we get some idea about how the structure of finite abelian groups works. And if you've just joined us, you might like to put your favourite number in chat, which is something we're doing today. Okay. Modules over polynomial rings, right, in this case. M is a module over, and we say it's over the associated scalars. Sure, it feels weird. The scalars feel like a bigger thing than they should be. R module over Z. Okay, so it says over Z, where Z is the ED. M over R. Okay, where R is the ring. Good. What's down here? Module over polynomial rings. Good. Okay, so that might be my second one. F's a field, and you've made a polynomial ring like that to get an ED. M is a vector space over F and considers the constant polynomials. Oh, goodness me. Multiplication by F now has the effect. Multiplication by F is an F linear map back into M, because you've got to define. Right, you've got to define what that linear map is, because this has to go from M to multiplication has to give me M objects, right? Where you go, so your ring thing, R across M to M. Okay, so you've got to decide what x means. So you've got your constant polynomials. They're fine. They've got to do f action on. They've got to do stuff to m. Oh, like a vector space with that field, with module over a field. And then you've got bonus extra. You've got these ones which must correspond to a linear map. Must correspond to a linear map. Just give me two inputs and it's going to be linear. Okay. The entire structure is then on the vector field for the vector space, which was that module over a field, and then p of x is going to be p of t because you do linear combinations of your linear map. Okay. Given a vector space and a linear map, define f as an fx module. Oh gosh. Are you going to define some sort of action over groups like differentiation or something? A linear map. Given a field F and a square matrix A. FA, this stuff is also weird. FA, so put A, no. FA, so this thing, what are these? I guess this is the name. An fx module where x applied to PA. This is too much for me right now, I think. FA is a different module to the fx module defined by A. The square bracket's taking over. This is third year of university, and it's oh no, this bit we're currently doing is second year. But don't worry, there's much stuff that comes before that. Welcome to chat, by the way. Hi. What's your favourite number? I'm guessing maybe 9127 because that's part of your username. Which is a nice enough number. Good. Rx module defined by A. I don't get this at all. I wonder how important these are. Okay, this example is too hard for me right now, but I'm going to put like exclamation mark. Don't get it right now. I don't follow all the square bracket stuff, and then there's a warning saying watch out, it really matters. Terrifying. Okay, 161. Given two R modules to form direct sum, component wise, good stuff. Generally for explicit, you can define that. Three modules, they just don't interact with each other at all. 162. If R is an ED and I is an ideal of R, then that thing is naturally an R module. Oh gosh. Oh, it is all polynomial ring stuff. I was hoping I could avoid them. Oh well. Scalar multiplication like this. Right, read it fast, then slow, then fast. You read it fast the first time to just see what's there, slow the second time to actually understand it, and then fast the third time to try and get to know it. The pattern there is tourist, explorer, local. The first time you're a tourist, you're just looking at what's there. The second time you're an explorer, you're trying to like explore all the nooks and crannies and really get to know it. And then you're a local. Third, you go through quickly without looking at anything. Tourists just come through, snap photos, move on. Explorers go through and actually look at the details. I'm on my first time through, so I've got to be tourist, right? Scalar multiplication, applying to numbers. X happens twice. It's kind of quotient by this polynomial. So multiplication works like this. So these are isomorphic. So there's kind of a way to turn the kind of polynomial questions we've been doing to turn them into matrix groups. Okay. Well, we already know that one's QI, right? Okay. We had some examples like this earlier on. Okay, isomorphic is our modules, modular morphism. Ln of e to the e. Is that just e? That definitely looks like it might just be e, because that's log base e. Anyway, good times. Okay, modular homomorphism if it respects those things and those things. No phi of r there because phi is just a map from M on the M's. R, they both have to be R modules with the same R. Okay. Phi is phi bijection, fine. Group homomorphisms, linear maps. Find all the modular homomorphisms sounds difficult. E is a nice number. I agree, and if it's Sean's favourite number, then there we go. Solve complicated. Might note multiplication by x is away this matrix. Ugh. Multiplication by that matrix. Profound those which, oh gosh, companion matrices. Why are there limited modular homomorphisms? There's not that many. Something to do with the Galois theory stuff about us moving groups around or something. Structure of modules. Note that scalar multiplication by this is the same as scalar multiplication by 0 as this thing is 0. Not the case, as that thing is non-zero. Okay, I feel like this example is a helpful way to actually get a handle on how these modules work. Let's just go through them one more time. So the module, what is the module here? So it's a group of matrices with addition, I think. But then multiplication means multiplying by R. Every element of this can be written like that. I think. Why is there an I here? Oh, because you can add on. You've got to decide what it means for. Oh, this group. The group generated by C? How do we get into the matrix then? How do we get into the matrix? Down here, matrix stuff. No matrices here, just the matrix here. FA means, so like RC means an FX module with X of P of our A. What's P? Any polynomial multiplied by X. I can only imagine multiplying A by reals. I can't imagine what this is kind of actually doing. Linear maps. There's some linear maps in here somewhere. Can't see them. Oh, bye, Ashwinda. Take care. Have a good weekend. I haven't really grasped what these are, but that's fine. Elements look like, apparently the elements look like this. Okay. Isomorphism theorem, classic. Yep. The kernel is submodule, image is a submodule. Qx module, q squared. Oh gosh. Okay. More examples. Linearly independent. If the only solution is that, generate like a vector space, right? Form a basis, finite generated. Module with a basis. Most modules don't have bases. Wow. Okay. Basis for Rn for any R. Z2 is linearly independent, but not a basis. Okay. Z is not free. Z2 is not free as a Z module. Crikey. Z2 is free. Any basis of Rn contains elements. Adds with rank. Okay. Skip the proof. A submodule of R is finitely generated. Seems fine. Skip the proof. 179. A submodule of Rn is free and has small rank. Fine. Important difference between the theory of vector spaces Most modules don't have bases. Linearly independent set cannot always be extended to a basis, even if it did have a basis. Spanning set doesn't need to contain a basis. Oh, these are all very annoying. A proper submodule, a free module can have the same rank. Cyclic is generated. Fx is generated. It's called a cyclic vector. Okay. Cyclic Z modules, the cyclic groups generated by a single element. Okay. Square matrix. What is group? The underlying group? Okay. There's an underlying group here. Square matrix A over field F. This is a cyclic module as it is generated by I up to... Okay, haven't understood what it is. Still haven't understood what it is. It's generated by I though. Under ring stuff, what are you doing to I? That's got anything to do with A. Generated by I. Back down, back down. Generated by a single element. And the map, right? So generated by includes the kind of map where you decide what. So in the polynomial ring, you've got f of x. You've got to decide what x does, and it's going to take x to maybe, let's say, a, and then that generates everything. So you've got to, you decide where I. So this action of f of x in general on there gets you up to everywhere. So then if A is this, it's not cyclic. MA of x is x squared minus 1. The minimal polynomial is that. And so for any v, cubed is if it generates, oh my goodness, the inner product. It's not R3. Oh my goodness, some of the planes as submodules generated by those, we decompose it. Crikey. 185 down here. I'm trying to race through and have a look at what's here. Fx structure defined by T for V going to V. Individual vector space over F. Scalars for F. With an Fx module structure defined by what does X mean? Linear maps. Okay, pick a linear map, that's what X means. Defined by T. Okay, so V is cyclic. That's an Fx module. And then V. Oh, is that what the X was doing for that polynomial earlier? Or some P earlier on? Vectors like this form a basis. So that V is cyclic as an X. Okay. With respect to the basis, it's this. And the minimal and characteristic polynomials of T are both that. Companion matrix. It's called the companion matrix of f of x. Skip the proof. Something else spanning. Okay. Just making that basis. And then proving it's minimal polynomial. Okay. Given a marginal assumption and from the quotient thing by looking at the cosets. Ooh, with coset algebra. Expressing a modular quotient to make transparent the module structure. So this is isomorphic to the Rx module defined on R by minus I1 on R. Minus on I1 is minus 1. Rationalize about knowing the scalar multiplication by x acts in the same way as multiplication by minus 1. Oh, this is like banning x plus 1, so x on I1 on the identity means, so this is like R acting on something from M, x acting on the identity means the same thing as minus 1 acting on the identity, which is minus the number minus 1. Okay, not sure I understand the structure anyway. Chinese Romano theorem, okay. Any polynomial P of x of fx. This is a cyclic fx model generated by 1. Oh, wow, okay. And there's an isomorphism theorem. A map like this is a module isomorphism onto the image of phi, quotiented by the kernel. Okay. Almost identical. Extra line to check that the R module structures align. Here is the again. Given the nature of the homomorphisms we found between them, RC is this, given by PC polynomial plus that by that in a similar fashion as that decomposition can explicitly and transparently the Rx module structure because of the direct sum. Module is a lot more straightforward and the answer a lot clearer. Note, for example, that x applied to alpha beta is this, very easy. Modular homomorphism from there. In particular, an R linear map, so it's determined by phi 10 and phi 01. Whew, okay. Say that that's AB and that's CD. We have this. So, why are all these things 0? Oh, because we've got these things on the left and we've got the images on the right. We're moving the phi's around, right? Phi respects this. So we can move the action of x inside, I'm calling it action, but we can move the effect of x inside phi, and then look at these things. Those are supposed to be equal, so yeah, okay, everything's 0. And A could be anything. Oh, and then it follows through that you multiply a general point alpha beta, you take A alpha. Scaling and a collapsing. Scalar multiplication by x in RT and never corresponds to multiplication by 2 as it does in the second summand RC. Okay. Right, return to this Rx module. Ideal is not cyclic but can be decomposed as the direct sum of the x-axis and the y-z plane, which is cyclic submodules. Somewhat more transparently read module structure by writing M1 as that and M2 as that. R over generation of R is this. I don't quite understand how maybe it doesn't matter what you have to specify what the x corresponds to in this structure. Where does it go? Maybe it doesn't matter. Maybe that's just specified by saying, oh, there is some linear map A. I1 is going to get sent to somewhere. Polynomials. Okay. Anything down here? Nothing down there. What's over here then? Oh, Smith normal form. Amazing. Presentations. Skimming through, let's go. We're going to make it a 5, aren't we? Can you invert a square matrix? I can try. Equivalent. PAQ is B. Okay. Yeah, sure. Multiplication. Not invertible over Z, but would be over Q. Okay, so yeah, matters. Oh, say QX, fine, okay. Yeah, okay. Smith normal form. Let A be an n by n matrix, then there exist elements D1 up to DR known as invariant factors. Unique up to multiplication by units such that A is equivalent to, there are P and Q like this, diagonals here, zeros everywhere else. Where, oh, the D1s divide each other. Lovely. Proof, oh yeah, right, ECOs. This. Okay, step, ECOs, EROs. Corollary. M be a submodule of R and then there exist elements where R is the rank of M1 on a basis of Rn such that is a basis for M. Oh my goodness. And big comma basis for Rn such that that is a basis. No, maybe there exists, yeah, there exists elements D1 and a basis for Rn such that this thing is a basis for M. Where D1 to DR are elements of the module? No. Summation R to the n. Rn times. Vector space, so R, where you could bring in R as the kind of scalars, and that's fine, it's a ring. Yeah, okay, multiply component wise. So okay, I guess when I see R to the n, I need to imagine vectors, and also, by the way, the scalar is also R. Okay, so that's supposed to be a basis of D1s. Sigmoid's correct finds apply the method of the following matrix. Put that matrix into Smith normal form. Off we go. So then after a lot of work, 1, 10, 30. Also able to answer the following. So after a lot of work, it said 4 such that that is a basis for that. Proves calculation. Column headings. Ooh, doing those row operations. Still a basis for set 4. So we began with the basis need. Column operation is invertible. Still span hammer now. Clearly independent. So we've shown that. We can take F1 to be that, F2 to be that at the top, F3 and then F4 to be E4. It's a basis for Z4, and F1, 10, F2, 30, F3. It's a basis for M. Huh. Do some cool stuff with matrices. Equivalent to a basis. It gives you a basis. More examples, more modules. It's not free. It's got, for example, relations. It's not just the direct sum of some stuff. Oh, this is not free. 2A. Oh, these are cyclic. This one just R plus R plus R. Characteristic 0. Could show other generators for M1 as A and B plus C. There's some isomorphisms. Every relation involving A and B plus C can be deduced from 2A equals 20, B plus C equals 0. Those relations share all relations. Again, A, B and C are generators. Or again, might have been generated by M, B plus C. Oh gosh, okay. Can be captured in presentation matrix. Columns in the first matrix. A, B, C. Just seeing what's there, just seeing what's there. Relations generator. Relations next one comes to Curve. Giving your generators every element feels like a basis. There's more of this than I thought. Quotient of a free module, fine, okay. Some module of the finite generated module is finitely generated. Sounds obvious. 4 lines. Skimming it. Some module of free. Ambient R module. The relation module is finitely generated. Presentation matrix. Kernel is free. Oh gosh. Yep, relation module is finitely generated. Kernel of phi. Phi being that map we just had. Seeing what's there, seeing what's there. Map onto homomorphism. Thinking about like going from a basis onto the generators. I knew they looked like a basis. Okay, missed that. Module is blah. Smith normal form. To get 414. Okay. 26 elements of order 3. Form. What? Z3, Z3, Z414. 26 elements of order 3. Order like that. Without all being 0. This is mad. What is going on? Order 3. Oh, picking up the things from here. You got choices, choices, choices. Multiples of 3. You kind of pick them up along the way. Okay, okay. I can sort of see where you're going with this, maybe. Okay, once again, this RX module. Not cyclic, but has generators. Relations are sufficient to generate all relations. So some relations. Okay. It's isomorphic to this. Goes on to there. Here's the image. Isomorphism. Given a vector space VO for f basis like that, defined as an fx module via matrix A, V is generated with these and we have some relations. Fast, slow, fast. Given V is c cubed. Find generators for V. Generators on the left. First column represents that. I've no longer got really any idea what's going on. Classic. Defined by T is like this. We're splitting things down. We're factorising things. We've got some generators and relations. I kind of missed that a lot. Structure theorem at the end. Torsion element. If you can act on with R to get zeros, so I should imagine for the group stuff, it's like the order of a group, order of the element maybe. I mean, yeah, I think order of the element. Have torsion if it has any non-zero. Torsion free if zero is the only torsion element. Okay. They form a submodule. Here's the quotient. Quotient is free. Note that zero's in here. Then R2 is non-zero. We have this. Oh, what am I doing? I'm reading a proof of this stuff. Skip the proofs. Module isomorphisms in there. Right, and there's a structure theorem for finitely generated modules coming up here. M finitely generated R module, then find non-negative integer R called the torsion-free rank of M, and non-zero non-unit elements as invariant factors such that those work out, and such that M looks like R to the R direct sum with all of these quotients. The rank is unique, and those D's are up to unique up to multiplication by units, with these things dividing in that order, like in Smith-Normal form. M is finally generated by these. The unique module homomorphism. This is how it works. Module homomorphism mapping from Rn onto M. Look at the kernel. By the corollary to Smith-Normal form, we know there's a basis for Rn and Dn. Di with like this. Load of trivial groups added together, and hence we have that thing, but those things are sort of some Chinese remainder theorem stuff going on here maybe. These are not co-prime, right? I don't know, then the integers aren't, but add any of these, we could just omit those. R to the n minus k there. Now note that dkm, because dk R to the R is a free module, so the rank of M is uniquely determined. Right, you can sometimes do rank stuff on M. Pretty unique factors. Example. A, B is in the required form because it's already cyclic. Generated by 1. This is mad. All of the modules above have 0 rank. So you've got to go 220, you've got to rewrite it as things. These are co-primes, bring them together so you've got things that divide the next one up. 6, 12, 16, you go. So you split them, you're splitting them. 2, 3, 3, 4, 16. And then you put them together into factors. 2, 3, 3, 4 to make. I don't understand at all. I spun them around and pieced them together, kind of increasing factors. Alternate form all look big direct sum. So we've seen sigma, we've seen big pi. Now get ready for big direct sum. Alternate form of structure. Minimal decomposition into cyclic submodules. Feels like Kappa theory again. That's decomposition stuff. Subsequent decompositions. Elementary devices. Oh gosh. Write all of that. Multiplication by units. Uniqueness. Okay, you're not reading that now. Argument made for a specific Z module. 8m is 0. apply 8 to this, that means keep going 8 times and you get 0 back again. Okay, 4m is 2 squared, that is. Dimension 2 is the number of Z8 subhands in the thing we were looking at. There's a quotient. Oh my goodness. So, finally generated abelian groups are down here. Unique non-negative integers. This is simply a statement of the structure theorem for the Z modules. Quotienting Z by the ideal, kind of sub-ideal, and those ideals were NZ. So those are then isomorphic to these subgroups, says they are. 360. Okay, so you've got to write an increasing sequence like this, where each thing's a factor of the next one. 2292, yeah, with these like this, dividing each other. Elementary divisors of these groups. Big gap, 2495. I don't know what that means. Elementary divisors. Let's now note that these things are the same. Oh no, what were these? These are all isomorphic. 40, 45, 2, 180. This is the second listed group. It's got the same elementary divisors as that one. 490. 90s. Not a multiple of 4. If not explicitly on it. Ah, right, okay. Which is isomorphic? Because this is an abelian group of order 360, so it should be on your list, but it's not in the form, it's not explicitly on my list because my list goes like this with D divisors. And I can split it up, right? So Z90, the way you split that, you can split it into coprime bits, and then you can join together coprime bits. Right, okay. Identify the abelian group generated by a 4-element subject to following relations. Excellent stuff. And then EROs, ECOs, and it's that one again. So Z10, Z30, Z. 2 elements, order 3. Oh, this is lovely. And then finally, some rational canonical form stuff. Matrices. A is similar to a matrix of the form. I'm trying to learn modular theory by just looking at it really fast and seeing how much of it I can get in my head. So there's an interesting way to learn maths that's maybe not working. And we're going to wrap up quite soon, I think, but I've been saying that for the last 2 hours. Venus normal form, how much do I care about this? Not a huge amount. Matrices. I came for the finite abelian groups, I think. Proof involves splitting this up. Every element's a torsion element. Rank 0. Every element's a torsion element. Sounds quite cool, doesn't it? Loads of proof about splitting it down. Jordan normal form, I remember vaguely from university, somewhere in 2nd year. But here's a proof using modules. Okay, plot a form like that. Nullity, nullity, oh my goodness. The above says this, splitting down C to the N. Defined by C to the N on a matrix. On C to the N by A. Like if given a matrix, get a C to the X module structure. So you need the C to the X notation, you need the C to the N, and you need A. Elementary devices look like this. Okay, and more proof. Ordered basis, and the Jordan blocks look like this. Just a bit nicer form, just as commonly used. And there's an example to work out the normal forms of these matrices. And do that, find a minimal polynomial. Looking at rational canonical forms via some matrix argumenty sort of thing. I have no idea what's going on. More examples over here. Bases and expressing, my goodness, the incredible mess with this particular module. Is that over a particular ring defined by a particular map? You have to decide what the X map means, right? V and that T, they don't find the, yeah. So we can't found it, it doubles up. Okay. Not sure how much I care about Jordan Moore before at the end, but I would like to get a little bit into some of the objects in classification theorem. So this is, I do care about finite abelian groups. There's a little bit in the Galois theory notes where we realise that something has a abelian quotient, and then we say, well, why not split it down into its components? This is the theorem that really I would like to try and get to. This is my new mission, I guess. It's no longer quite a quest for the Quintic so much as a quest for the classification, which is not as snappy. If anybody can think of something that sounds like classification and means mission. Yep, no, I'm out. Right. So this is a statement of, so I've sped through to try and see what's in the notes, and now I'm going to go through slowly to try and learn things. And it's tough because I've got to get some understanding of what a module is, which is a totally new structure that I technically learned at university but didn't keep in my head. Cool, okay. Welcome back to Twitch Learns Maths, a new maths show. I'm your host, and I'm learning some maths. We're going to work backwards a little bit to put this in context so we can see it coming. Here's the big target thing we want to learn. I don't think Twitch is going to play along so much as just see what it's like trying to learn stuff, right? Learning is hard. So we're going to find the structure theorem, and we want to understand what a Z module is. If we can do those things, then we're doing pretty well. Now, I remember on my run through the first time round, there was all this stuff in between, but we could look at the structure theorem here. Finitely generated R module. Now, that my Z module is finitely generated. If it's a finite group, then yes. There exists a non-zero R called the torsion-free rank, and non-zero non-unit elements known as the invariant factors such as this and these. Now, if it's a Z module, then all these R's will be Z, and these, I think these ideals will be, these ideals of the ring. So I should think about Z quotiented down, those are the things I just saw. And there's something about torsion going on in here, which is only just defined up previous page or something. Okay. So structure theorem says that we can do this. And it uses Smith normal form, which is a clever way to write a matrix. I would like to understand what the matrix has got to do with abelian groups at all, right? I can sort of see how Z acts on the abelian group. I'd like an example. I can sort of see how Z acts on an abelian group, but then not where all of the Smith normal form matrix stuff came from. I think that's the idea that I'd like to try and grasp. The thing I'd like to try and get in my head. Okay, welcome back to Twitch Learns Maths. There's going to be some isomorphism theorem stuff. You might need to know what a torsion element is. Okay, the main thing I think I want to know where these matrices come from. So if I ignore Smith normal form for now, and just take it as, oh, if you've got a matrix, there's this nice thing you can do for matrices. Let's read that about Smith normal form. Yeah, so Smith normal form says, it takes you on the following bit of journey. If A is a matrix, then you can find these invariant factors such that A is equivalent in the sense that the PAQ is equal to this. It's equal to this, where it's mostly zeros and some diagonal stuff down there. So that Smith normal form is sort of adjoint, it's about matrices. And the proof in here is very, very matrix themed. Right? Yeah. Invariant factors. Lovely. So going to use the other sort, the Jordan normal form as well? Maybe, maybe not. Here are some matrices. Okay, so we'd like to understand this. In particular when R is Z. So if in doubt, R is Z. And we're going to back up to the definitions over here, we would like to understand Z modules, abelian groups, finite Z modules in particular. Same mission though, same sort of strategy we've been using all week on the quest for the Quintic. Read through quickly, find out which bits you need to understand the most, read through slowly, focusing on those bits, and then go back and fill in some details, then really quickly to see if you can get an overall picture. We're now testing out whether I can actually do a study with me live stream with study tips. No longer on the Quintic. Oh, it feels weird. What am I doing? Should I turn off the graphics? Is this a new quest? Should I draw a new map? Yeah, a little map here. We're gonna go, so map that we just saw, modules. It's gonna be a boring kind of timeline map, I think. Modules, we want to go like Smith's normal form, but that seems not that exciting. Which then just goes to the structure theorem. I know this is just like writing out the section titles from the notes, but just reminding myself what's coming up. Matrices? I can't spell. Matrix? When did we go into the matrix? Modules including groups. Okay, so let's try reading this now that we know that we're motivated mostly by, to start off with at least, Z modules. So you've got an abelian group. I'm going to imagine that's my target abelian group. And it's together with scalar multiplication. How do you multiply an element? And it says down here how you multiply a group element by Z. You're going to do some adding. You're going to keep adding. Okay, I can imagine that. So example, I've got my Klein 4 group. Yeah, let's do the Klein 4 group or something. 1, everything's got all of 2 in the Klein 4 group, that's silly. So let's go 1 r squared. VPN, which is the cyclic group. S3, rotations and reflections. Then we can act on that. So Z cross with this group to G given by, oh I see, okay, so I need to decide what's going on for all integers and for all of my group elements. 1r squared VPN, and I can do this action entirely determined by the abelian group structure, because this has got to be 1 plus 1 plus 1 plus 1 m, just 1m plus 1m plus 1m, m plus n plus n. So we're doing plus as my group, so my group has plus in the group. So then down here it's going to be 1 and 1, 1, 1, because plus means repeated function operations in here. This is going to be r, do it again. Plus means do it again, m and do it again. R cubed is 1 and then r squared. So this is powers going down. It's not too bad, not too bad. VPN goes to, so z equals 1. So yeah, okay, which number are you dealing with? VPN 111, VPN 111, and then when I get down to 6 it'll loop around again. Okay, so eventually, because g to the mod g is equal to e for all elements of the group, that's I think Lagrange's theorem, eventually you loop back around again and you get things where you get back. I've been calling that 1. I've got a feeling we're going to say it gets back around. So it exists an n such that an n in z was inverses as well, such that n applied to g multiplied by g is equal to 0. Is I think how we're going to call it if we're thinking about it being addition in the group. Trying to get my head around the notation. Trying to work out a little example. I've picked my own favourite abelian group. I know it already says example, But even if it says example, it can help you to get down to an abelian group. You should maybe think about a particular abelian group if you want to try and work out what's going on. And I've done a little bit of calculation. It's very, very messy over here, but that's me trying out a calculation. Okay, now, I think I do need to understand these modules over polynomial rings, which is a bit of a shame, but hey. Over a polynomial ring to mean those are the scalars for my vectors, for my module. Can I call them scalars for my module? Scalar multiplication, yes, at the top. Ooh, learning words. Twitch does maths. Okay. M is a vector space over F. Crikey. Vector space over F. We've got a field. F is a field, so you do pick up a vector space just by having coefficients in F. That's just what a vector space is. Yep, and then multiplication must do a linear map because this has to send R cross M to M, and we've got this X in here. So this is an example for a particular X. That's got to send, if I fix the element of R to be the polynomial X, it's got to send M to M, and then there's some linear combination stuff going on top of that. Okay. Entirely dependent on T. It's about module axioms. Yeah, cool. So then it's going to respect it afterwards for any polynomial. So that's P for any polynomial. Conversely, given a linear map, define M as an fx module by defining scalar multiplication like this. So once you've seen your linear map, what's it a linear map on? M to M. M is the group, kind of. M is kind of like a group. So T is like M to M, where M is the sort of group or module map, self map. Okay, I might call it an automorphism if I'm feeling fun. Right, so down here I can see A. Given a field F and a square matrix A over F, then FA means this fx module with, for any polynomial P, I think, probably, x applied to P just means multiply polynomial by x and then plug in A. Maybe? Yeah. So I've got to decide what happens when a P could be an element of fx, maybe. So it's trying to describe to me what happens with FA means polynomials with A plugged in, I think. Yeah, okay, so this is polynomials of A. Polynomials of A, like 1 plus A, or 1 plus A squared plus A cubed over 3 or something with F the rationals here. So then what is X? FA is an fx module. So this thing is a group. It's kind of a ring, right? But we're also imagining FA itself as the group. And X is going to act on, yeah, okay, we're imagining this to be a group under addition maybe, which is kind of fine, sure, okay. So a group with plus. Group makes this plus. Sure, okay. And then X, we're imagining to also f of x comes along as a ring, and that says you should kind of just multiply everything by A. Okay, we're getting there, I think. Except no, it's in general, FA is a different module to the fx module defined by A. Fx module defined by A would be if that was the map associated with X. Gosh, this is tough, isn't it? It's really tough. Here's this one, which they keep using. The Rx module defined by A as the kind of T map, the map for A mapping, I guess R cubed to R cubed or something. It's a three-dimensional vector space. So, why is that? It's a vector space where brought in. Crikey, I'm now going to have to think about minimal polynomials of a matrix. Rx is defined by A as a three-dimensional real vector space. So I need to go back to the Rx module, which meant you could have multiples by R of here. What's the vector space? Oh, so that way the vector space would be triples, so things in R cubed. So I thought of real vector space, I guess, R cubed. That's the group here, and then that's the group, and with you've got this thing. So you could take a real and a vector. So there's like I should read this as M R cross M into M by scalar multiplication. So you take me any vector that lives inside M, and that's fine. I'll just multiply by scalar. So I take 1, 0, 0 or something and send it to 3, 0, 0. Brilliant stuff. I'm enjoying my scalar multiplication. Thank you. But then also Rx cross R cubed includes things like x of any vector needs to be AV, like that, which will send V to something like x applied to the vector ABC goes to A, B plus C, C. Oh, I think I saw some A's and B plus C's later on, so that's quite gratifying to see it again here in my own handwriting. Hooray! But that's all right. So that tells you how polynomials are going to act on this. I guess I could do it again, but yes, it was like three-dimensional space because just the real scalar multiplication in there is fine. By comparison, R of A, which I think I've seen more references to later on, looks like this. Wow. It's spanned by two-dimensional real space. No. Polynomials in A together with y not multiplied by another A. Polynomials in A look like I and then A, and then what is A squared? Question I didn't really have to answer over there because I got to keep all of the A stuff. This is 1, 0, 0, 0, 1, 0, and then 0, 2, 1. So I don't really understand what's going on here. Oh, so the combination is looking like I'm just going to add all of these things up, right, when I do my polynomial. The minimal polynomial. So yeah, so that is polynomials have been quotiented like this. It's the minimal polynomial of A. And there was some stuff earlier on in these notes that I didn't really pay much attention to about quotienting by minimal polynomial of matrix. So maybe I should go back and look at those. Okay, by A, but then this one is simply, so A squared for these people is simply, oh, hang on, here we go. 2A take away 1 is related to that. There's a minimal polynomial going on. Oh, I get it. Okay. So, yeah, sure. Okay. So it's your question about the minimal polynomial. And that's only a two-dimensional space because you get you multiples of I and you multiples of A. You've quotiented polynomials by a quadratic. So you get two-dimensional real vector space that is real vector space, not a field. No, because that's not an irreducible polynomial. Good. Okay. Oh, suddenly we hit. Whoa! Hang on. We're quotienting a polynomial ring by a polynomial. I remember that. That was highly relevant to all the Galois theory. Okay, seeing these things in different contexts. Amazing. Brilliant. Okay. Direct sum. I do want to understand one of those. Free modules are relevant later on. N times with, I guess, no restriction. Just here are m plus n, both R modules. Natural way is to do multiplication component wise, don't do anything silly. Okay, that's the structure of a two-dimensional vector space. This is something we've been doing. Scalar multiplication like this, x multiplied by 1 is x, and then x, no, replace it minus 1. So the multiplication is represented by the matrix. Right, here we go. Right, okay, it takes, and then this is like the vector format of these polynomials that we've been dealing with. So instead of, if I do that instead of 1, and if I do that instead of x, then I get this matrix for how this behaves. Everything becomes kind of linear maths. Linear maths in this world. Right, so you think, so when you have I as an ideal, then that quotient is naturally an R module. Now, you knew that when you did that quotient, what did I know you'd get? So it's ED, Euclidean domain. How do you get there? Not necessarily a field, because R is just an Euclidean domain instead of a field. No, but that, there's a ring here. This R question by I thing we've had loads of times, and apparently the R module has a structure of a two-dimensional vector space. But that's precisely what we've been doing. We've been forming this vector space. Okay, it's not a field if that's... In this case, it is like a field, unsurprisingly. This thing and QB are isomorphic. A plus B goes to A plus B, B. Yeah, not surprising, okay. Idea of a modular homomorphism. Cool. Okay, we're getting there. It's 4:45. Learning maths. I plus B, C, because I squared. Yeah, okay, it's two-dimensional at best. Two-dimensional like that over there. Okay. So initial matrix. Here's the matrix for how multiplication works. So like the stuff like the King-Banda polynomial. We're looking at how things behave in that world, sort of. Okay. Find all modular homomorphisms. Okay. And they have some things in common and some things not. So the homomorphisms are a bit limited. Okay. Consider R as an R module, submodule of R the ideals. Sure, okay. It'll be closed on the multiplication by everything. Closed by under addition scalar multiplication, so it'll be multiplication by all of R. Okay, all scalars. Modules of Z are the subgroups. Closed under addition, which is the group action. And scalar multiplication here means doing lots of powers of the elements, which is entirely determined by the group action, so that's fine. It's just closed. Scalar multiplication is just lots of addition in that case. Multiplication is just a lot of addition, not something I thought I'd say. So for Z, okay, so for Z, not for abelian groups, the substructure doesn't involve this kind of multiplication by a wider element because there's no sort of wider scalars. The wider scalar is just the integer kind of action associated with taking the element of particular power. I really like to think about groups as having multiplication. And here it's kind of bugging me that groups have to be defined like with addition, so that you've got spare multiplication notation for the scalars. Defining V as an fx module. Okay, so now we're back in the type where you've got a V T invariant subspaces. Okay, look, cool. You got these submodules. Defines a QX structure. Okay, I want to get through a bit. Linearly independent of the only solution that's finitely generated. If there's a finite subset that generates it, basis is called a free module. That's what a basis would look like for Rn. Okay, Z2. Z2 is not free as a Z module. Z2 is the cyclic group of two things. It's not free. It's 2 times 1 bar is 0 bar, but 2 is not 0. Because it remains the case that 2 bar is 1 bar, but now the scalar 2 bar is the 0 scalar. What's that? Free as a. Okay, read the free again. With a basis. Oh, so you've got no non-zero combinations, which might mean. So this would be a word for an abelian group to be 0. So the free module would be like the free group with no restrictions. They form the free word. As a Z module, this note about Z2 modules, don't mind about too much because 2 bar fine. If I'm thinking about Z modules, then there's kind of a free group on a certain number of generators. Yeah, sure, okay. Again, thinking about the particular case that I most care about is a handy way in. The notes are written so that you can apply them to lots of different cases. Different people can see different things in them. Base functor contains n elements. That's fine. That's the free group, right? Free module. Basis. Yeah, pretty sure it's the free module. Backup. Module with a basis. That one has a basis. Cool. Good. Okay. And then some facts about these bases being all bets are off as far as I can tell. Well, so here's 2 things. Some module is free. Of Rn is free and has smaller rank. Cyclic if it's generated by a single element. So are my groups cyclic? Probably not. If they're cyclic groups, good. The things I want to split things into. Okay. Okay. So let me think about these. Where are the matrices going to come from my abelian groups? Can't see it yet. It's the action of something. When you move to, you take some group action maybe, and that represents X in some sort of polynomial ring. Inspired module. There's so many words, right? So many words stuck together. Here's a cyclic vector. The vectors, those form a basis. Okay. No, there's a decomposition there, which I want to understand. Yeah. What's this? Any V in RV generates VAV, which is not that. So there's no cyclic vector defined on R3, and this is now the Rx module, not R of A, which was 2-dimensional. The Rx module does some stuff on different places. X-axis M1, the YZ mod plane M2 are submodules. Behave separately. They are A invariant subspaces and are cyclic. There are zeros elsewhere. And a cyclic is there respectively generated by I and K. Oh, that was cyclic. So you start with K, and then you apply. So A of 001 is 011, which then generates, if I'm allowed to do subtraction or something, 010 decompose to maximum cyclic. Having trouble believing that that was cyclic, but I suppose it all gets around. So this is a link between kind of normal form sort of thing and generating things cyclically within each bit decomposition. Still don't understand where the matrix is going to come from for my abelian groups. I think that is the last thing that I would like to see today. Move on for some future adventures in factorising abelian groups. Here is the companion matrix of f of x. This looks good. Maybe this is the matrix I'm looking for. Let V be an n-dimensional vector space over F. So if you've got n generators for your abelian group or something, n-dimensional vector space over F. An fx module, I do not have this for my groups, right? I do not have this for my groups. What would the fx module be? Fx module, not z module. Yeah, okay, sad. Well, you had T, and you could keep going round, and it's n-dimensional, so these form a basis or something. And then there's some coefficients over here, minimal and characteristic polynomials. Okay, cool. But doesn't seem directly relevant to where are my matrices? Definition to a quotients module, fine. Where are the matrices? Where do the matrices come into it? Splitting things down. Find me some matrices. Homomorphisms, lovely. Here are those ones again, splitting them down. Am I going to have to understand this as being something like it's going to hit Smith normal form now? I'm going to have to find out how to apply Smith normal form. Okay, where's the matrix for my cyclic group? It's the last thing I want to see. It's about 5 to 5 on a Friday. It's time to see some submodules. Trying to find some submodules. All of this looks super important, but we're going to skip it. Generated by some relations. Oh gosh. You've got some relations. So in general you're not dealing with a free group. Generally, you're not dealing with a free group. It's got some rules about what's going on. And the trick is to find out what those rules are, right? Chosen other generators. So maybe you've got like elements a squared is the identity, b cubed is the identity, and you're abelian, so you can always write things like this. bc to the 20 equals the identity. Maybe you've got some rules. Okay, getting there. Abelian seems to correspond nicely with the idea that your rules for the group might correspond with these kind of linear conditions or relations, whatever we're calling them. Okay, and equals the identity is a bit like the action being 0 under some sort of quotienting thing, maybe. If I look at the powers, and the powers is exactly how the Z thing acts. Okay, still not a matrix. It's a linear combination though, isn't it? It's linear stuff. I want to take those relations for my abelian group. Model's not free. Okay. So if your model's not free, then find some relations or something. Structure theorem, each module generators. Generators relation. Okay, I think I'm getting there with the matrices. 5 minutes. I think I'm about to see some. A finitely generated R module M with generators. There is an onto module homomorphism. Rn to M with relations in that corresponding to the kernel of phi. Okay. That looks like, yeah, okay. So this is saying take the generators for this group. Generators. Every element can be written in this form. Show me what's in your group. Finite abelian groups are definitely finitely generated, so these things exist, and there's some relations, possibly loads, but finally many things in the group. So you determine which things in your group are relations, which things hit the identity. Like how rotations in a triangle, you rotate the triangle 3 times, you get the identity. Reflections, you rotate it twice, you get the identity. That feels like sensible things to track. You also have rules about how the rotations and reflections interact. So there's all these rules about those reactions. It's not just the separate rotations and reflections. Otherwise, you could, if you didn't have any other rules, you could do this like, so if you've got R reflection and R is also rotation, people normally use S for S and T. So if you've got S for the rotations and T for the reflections in your group, then there's a rule for like S cubed is 1 is the identity in the group, and there's also a rule for the reflections, but there's also a rule for ST. Otherwise, otherwise you could just have something like this, and your group would be infinitely large if this never simplifies. For ST, 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 if it's just like never comes back. And in fact, that rule is that ST is the same thing as T inverse S. I think. Oh no, the other way around. Other way around. So rotate then flip. So if you hang on, it works like this. If you TST is supposed to be S inverse. What does that say? No. I think. And TSTS. This is not abelian. Lol. Okay. I should be thinking about abelian groups for my classification of finite abelian groups. Okay, so for abelian groups, we should worry about just powers like that. Or you could also have a restriction that maybe this thing's supposed to be the identity as well. That looks a bit suspicious. Does that form a nice group? So if I have, let me think about a slightly non-trivial group like, so C4 is generated by A with the rule A to the 4 is E, but the Klein 4 group is interesting. It's generated by A with A squared is the identity, B with B squared is the identity, and AB, I believe, is also like this, also has order 2. So then that tells you everything you need to know about your group. These are the kind of rules for generating the group. You've got A, E, AB, and you've got the element AB. And this tells you everything you need, because if I put an extra A on there, so the E element multiplies everything in some kind of sensible way. The A element squares to the identity, the B element squares to the identity, AB is the element AB. BA, you can read off from here, so these things were order 2, so you can multiply both sides to get AB is equal to BA. Yeah, it's insisting that it's an abelian group in a way. So then AB is also AB down here. AB is going to be times A is B. Wait, am I generating the cyclic group? No, this is not the cyclic group of order 4 because everything's got order 2. So I haven't screwed up. Everything's got order 2 in this group, which is kind of interesting. It's different from the group of order, the cyclic group of order 4. This one is C2 cross C2, and this one is C4. We're going to see in a bit those DLE possibilities. I'm now excited. Spent all time killing for time trying to get down to the end, and now I'm excited that we might be about to do something cool. Okay, generators that make your finite group and rules, you need some. So modular homomorphism from Rn into M, like this. Take me your basis vectors and send them to each of these generators, and then the action, there are some rules. Further, that's relation if and only if those are in the kernel. Gosh. Okay, something like that. Finitely generated model is isomorphic to a quotient free module. Sort of finite generators. Okay. So looking over here, where are the matrices? The matrices. Here are the matrices. Generated by A, B, and C subject to these relations. So this could be the rules for a ridiculous group, where I should read this as like A to the 6, B to the 18, C to the 12 if I'm using multiplication for my group, and that's the action of the integers on there. This is a Z module. Relations. Why are there Z's in here? Relations should be R's, right? I guess we're in a specific case. Oh, it's an abelian group. Oh, right, so this really is the abelian group that I wanted to talk about, with the relations on how those things work together. And there are 3 of them. Interesting. So, great stuff. There's the matrix then. To take that matrix for the rules about A, B, and C, how does this work? Solution. So cubes generated by those 3 things. particularly informative or transparent presentation. Whereas that's generated by those three vectors. Okay, here are some matrices. And if I want to understand how this quotienting down works, oh, look at it go. Oh, look at it go. That's some beautiful format down here. That's what the structure theorem's for. To simplify a group, to take the relations and to find the right combination of the relations to express it as this lovely direct sum of cyclic groups, which you can always do because Smith's normal form works. So second time through with feeling, knowing where to look, I've now got a motivation to go and put the time in to understand the structure theorem in general over here. Make these, understand this proof with these quotients in it. Thinking about Smith normal form along the way. And it doesn't look too bad. It's like a page. But I think I'm not going to do that on Twitch. We've got this somewhere buried inside the Galois theory notes. This use that you can simplify down. You got a horrible abelian group with some restrictions on it. Finite abelian group, then you can turn that down into some product, it's kind of direct sum of cyclic groups. Really good stuff. Chat, Twitch, it's been really good fun. We've been live for about 40 hours this week, which I would not encourage if you're considering doing some sort of live stream. You've kept me honest, made sure I did my work, gained some understanding of how Galois theory works, tiny bit of how Galois theory applies to other stuff, and a little bit of finite presentation of a little bit about the classification of finite abelian groups, which I've always wanted to know. Cool. Thank you very much, Twitch. It's been really fun doing maths with you, and I'll see some of you around for, well, everything else. Back to my normal job. Right, take care, chat. Bye. The quest is, as of 5 PM on a Friday, quest is over. Have a wonderful weekend, everyone. Take it, bye.